Welcome. Tonight we are going to spend 3 hours inside one of the most extraordinary ideas that the science of the last century has produced. The idea that the universe is not a collection of fixed, eternal, unchanging objects scattered across an infinite dark stage, but a living, evolving, transforming system in which everything, from the smallest dust grain to the largest structure in existence, has a history, has a birth, has a middle, has a fate. We are going to talk about galaxies. Not galaxies as decorative features of the night sky, not galaxies as the pretty spiral shapes in the photographs that have decorated a million posters and screensavers and book covers. We are going to talk about galaxies as what they actually are. The fundamental units of cosmic structure, the great gravitationally bound islands of stars and gas and dark matter within which almost all of the universe's visible matter is organized, and which have been changing, transforming, evolving, building, colliding, and quieting across 13 billion years of cosmic history. The transformation of galaxies is one of the slowest processes in the universe. A galaxy does not change on any timescale you can watch. You cannot observe a galaxy evolving the way you can watch a storm develop or a tide come in or even a star flicker. The changes happen across millions and billions of years, visible only to telescopes that can look far enough into the past to catch different galaxies at different stages of their development, or to computer simulations that compress billions of years into images that evolve before your eyes. But the changes are real, and they are profound. A galaxy that existed 1 billion years after the Big Bang is almost unrecognizable compared to the mature, structured, often quiescent galaxies of the present day. The history of the universe, in one important sense, is the history of how galaxies formed and grew and changed, how they acquired their structures and lost their gas and merged with their neighbors and settled, gradually, into the relative calm of the present cosmic epoch. You live inside one of these galaxies. The Milky Way. A large barred spiral galaxy, one of the more massive members of a small cluster called the local group, sitting in a minor branch of a filament of the cosmic web in a universe that is 13.8 billion years old. You are not merely an observer of galaxies from outside. You are an inhabitant of one. The light you see when you look at the Milky Way's band stretching across the night sky is the inside view, the view from within the structure, the perspective that no external telescope can provide. Tonight we will explore the full arc of galactic evolution, from the first proto-galactic fragments assembling in the dark ages to the long, slow future in which our own galaxy will merge with its nearest neighbor and eventually fade into the silence of the degenerate era. We will meet spiral arms and supermassive black holes and galaxy collisions and cosmic quenching in the deep field images that let us see the universe's childhood. We will understand, by the end of these 3 hours, not just what galaxies are but what they have been and what they will become. And in doing so, we will understand ourselves a little better. Because the story of galaxies is, in the most direct physical sense, our story. We are made of the products of galactic evolution. The carbon and oxygen and iron in our bodies were forged in stars that lived and died inside this galaxy over billions of years. The specific location of the solar system and the Milky Way's disk, the age of the sun, the composition of the Earth, all of it is a product of the Milky Way's particular evolutionary history. We are what this galaxy made, at this moment in its long, slow transformation. Let us go meet it properly. If these long, contemplative journeys through the science of the cosmos are something you value, please take a moment to like this video and to subscribe to this channel. It means more than I can easily express to those of us who make these things, who choose the slow pace and the deep dive over the quick and the spectacular, who believe that the best way to experience the universe is not in 30-second clips but in long, quiet hours of unhurried attention. And leave a comment. Tell me where in the world you are tonight. Tell me what the sky looks like from where you are, whether you can see the Milky Way or whether the light of your city has swallowed it. Tell me whether you have ever looked up at the band of the galaxy and felt the particular sensation of being a small creature inside a very large structure, like standing in the nave of a cathedral so vast that the walls are invisible in the dark. I read every comment, and I find them moving in ways I did not expect when I began making these videos. You are all, every one of you, inside a galaxy right now. The same galaxy. The Milky Way wraps around all of us simultaneously, regardless of where on Earth we are listening from. We share a galaxy. That is a strange and lovely thing to notice in the dark. Let us prepare, before we descend into the deep history of galaxies. Find your most comfortable position. The one your body knows, the arrangement of limbs and weight and warmth that signals rest, that permits the voluntary release of the small, constant muscular tension that holds you upright and ready through the day. Let that tension go. Let the surface beneath you take your weight entirely. Let your hands uncurl. Let your jaw relax. Let your eyes, if they are not already closed, close. Dim the lights or extinguish them. The galaxy outside is not visible through most city windows, obscured by the light we ourselves have put into the sky, but in the dark of your room something of that larger darkness can be felt. A permission to be small. A reminder that the ordinary scale of daily life is not the only scale there is. Take a slow breath. And as you breathe, consider this. The oxygen entering your lungs right now was released by a star that died before the sun was born. The carbon in your body was forged in stellar cores over billions of years. The iron in your blood was scattered into the interstellar medium by supernovae that occurred in this galaxy long before the solar system existed. You are carrying, in your atoms, the record of the Milky Way's chemical evolution across cosmic time. You are not just inside a galaxy. You are made of one. That is the frame for tonight. Hold it gently as we begin. Before we enter the story of galactic evolution, I want to offer one more orientation, a reminder of the scales involved that I think is essential for truly feeling what we are about to discuss rather than merely knowing it intellectually. The Milky Way galaxy is approximately 100,000 light-years in diameter. A light-year is the distance light travels in 1 year, approximately 9.5 trillion kilometers. 100,000 light-years. If you could travel at the speed of light, it would take you 100,000 years to cross our galaxy from one side to the other. The fastest spacecraft humanity has ever built, the Voyager probes, travel at approximately 17 kilometers per second. At that speed, crossing the Milky Way would take approximately 2 billion years. The Milky Way contains between 100 and 400 billion stars. If you tried to count them at 1 per second, it would take between 3,000 and 12,000 years to finish, roughly comparable to the entire span of recorded human history for each star in the most conservative estimate. And the Milky Way is not an unusually large galaxy. It is a fairly typical large spiral galaxy. The observable universe contains an estimated 2 trillion galaxies. 2 trillion objects, each one comparable in scale and complexity to the Milky Way, scattered across a sphere 46 billion light-years in radius. These numbers are not meant to overwhelm. They are meant to calibrate, to set the stage. Because the story of how galaxies change over cosmic time is a story that operates on all of these scales simultaneously, from the quantum fluctuations that seeded the first density variations to the large-scale cosmic web that organized the distribution of galaxies across billions of light-years. From the first hundredth of a second after the Big Bang to the trillion-year future when the last stars in our galaxy's remnant will be going out. We will navigate these scales together, slowly, one chapter at a time. And we will start at the beginning. Or rather, just after it. Close your eyes, if they are not already closed, and imagine looking down at the Earth from space. Not from 100 kilometers up, the altitude of the International Space Station, where the curvature of the Earth is just becoming visible and the atmosphere is a thin blue line against the black. Imagine looking from much further. From 1,000,000 kilometers. From a distance at which the entire Earth is a small blue disk, the continents and oceans visible as shapes of color, the swirling white patterns of weather systems moving slowly across the surface. From that distance, the Earth is an island. A bounded, self-contained object, clearly distinguished from the space around it. It has edges, in the sense that there is a place where the solid or liquid matter ends and the space begins, even if the atmosphere tapers gradually rather than cutting off sharply. It is recognizable as a thing. A whole thing. A galaxy is something like that, but at a scale so much larger that the analogy can only be gestured at rather than fully drawn. A galaxy is a bounded, self-contained collection of matter, stars and gas and dust and dark matter, held together by its own gravity against the expansion of the universe, clearly distinguishable from the intergalactic medium that surrounds it, recognizable as a whole thing even from distances of millions of light years. But where the Earth has a hard surface, a place where rock meets vacuum, a galaxy is only the soft edge of a gravitational boundary, a region where the density of stars and gas gradually tapers to nothing, where the last gravitationally bound members of the system shade imperceptibly into the emptiness of intergalactic space. A galaxy is not sharply bounded the way a rock is bounded. It is bounded the way an ocean current is bounded, by the physics of its own dynamics rather than by any material wall. And inside that soft, gravitational boundary, the galaxy is not uniformly filled. It is structured. Elaborately, beautifully, asymmetrically structured, with dense regions and sparse regions, with spiral arms and central bulges and outer halos, with clusters of young stars and ancient globular clusters, with molecular clouds that will become stars and remnants of stars that have already died, with a magnetic field threading through the interstellar medium and cosmic rays streaming through it and radiation fields from millions of stellar sources crossing it in every direction. A galaxy is not a simple object. It is an ecosystem. A bounded, self-regulating, evolving ecosystem of matter and energy and gravity and radiation, operating on timescales of millions to billions of years, changing so slowly that any individual observer embedded within it would not notice the change in 100 lifetimes. Every galaxy in the universe, from the smallest dwarf spheroidal galaxies containing only a few million stars to the enormous CD galaxies at the centers of rich galaxy clusters containing many trillions of stars, is assembled from the same four basic ingredients. Understanding these ingredients is the foundation for understanding everything that follows. The first ingredient is stars. Stars are the visible component of galaxies, the sources of the light by which we observe them from across the universe. A galaxy's stars range in mass from about 8% of the Sun's mass, below which an object does not sustain nuclear fusion and is called a brown dwarf rather than a star, to perhaps a few hundred solar masses for the most extreme objects. They range in age from billions of years, the old red stars in the halos and bulges of mature galaxies, to a few million years for the young, hot, blue stars being born right now in star-forming regions. And they range in their stage of life from newborn protostars still shrouded in their birth clouds to stars on the main sequence steadily burning hydrogen, to giants and supergiants in later evolutionary stages, to the remnants of dead stars, white dwarfs, neutron stars, and black holes. The stars of a galaxy are not randomly distributed. They are organized by the galaxy's gravitational field and by its history into characteristic structural components that differ between galaxy types. Spiral galaxies like the Milky Way have a thin disk of stars, gas, and dust in which ongoing star formation occurs, organized into spiral arms, a central bulge of older, more densely packed stars, and a diffuse halo of very old stars and globular clusters extending far above and below the disk plane. Elliptical galaxies have no disk and no spiral arms, their stars distributed in a smooth, roughly spheroidal distribution with little ongoing star formation. The diversity of galaxy types is, as we will discover, largely a reflection of the diversity of galactic evolutionary histories. The second ingredient is gas. The interstellar medium, the diffuse material that fills the space between the stars within a galaxy, is composed primarily of hydrogen and helium with trace amounts of heavier elements, in various phases depending on the local temperature and density. Cold, dense molecular clouds, where temperatures drop to tens of degrees above absolute zero and where hydrogen exists as molecular H2, are the nurseries of new stars. Warm neutral hydrogen, at temperatures of a few thousand degrees, fills much of the disk of spiral galaxies and is the reservoir from which molecular clouds form. Hot ionized gas, at temperatures of millions of degrees, fills the halos of galaxies and the space between the disk and the halo. And extremely hot plasma, at tens of millions of degrees, fills the intergalactic space within galaxy clusters, visible in X-ray wavelengths. The gas is both the fuel and the product of star formation. Stars form from gas. When stars die, they return gas, enriched with the heavy elements forged in their cores, to the interstellar medium. The cycle of gas flowing into stars, being processed, and being returned to the interstellar medium drives the chemical evolution of galaxies over cosmic time, gradually enriching the gas with carbon, oxygen, iron, and the other elements of the periodic table. The third ingredient is dust. Interstellar dust, tiny solid particles typically a fraction of a micrometer in size, composed of silicates and carbonaceous material and ice, is a minor constituent of the interstellar medium by mass but a major influence on the appearance of galaxies and on the physics of star formation. Dust absorbs and scatters visible light, making dense molecular clouds opaque and reddening the light of stars seen through it. It re-radiates the absorbed energy at infrared wavelengths, making star-forming galaxies bright in the infrared even when they are obscured in the visible. It catalyzes the formation of molecular hydrogen and other molecules on its surface. And it is a tracer of the cold, dense regions of the interstellar medium where star formation is occurring. The fourth ingredient, and by far the most massive, is dark matter. The dark matter halo of a galaxy contains several to many times the mass of all the stars, gas, and dust combined. It does not interact with electromagnetic radiation. It neither emits nor absorbs nor scatters light of any kind. It makes itself known only through its gravitational influence on the visible matter and on the trajectories of light passing near it. But its influence is pervasive and fundamental. Without its dark matter halo, a galaxy's stars would not orbit at the speeds they are observed to orbit. The galaxy would fly apart. Dark matter is the gravitational skeleton of every galaxy, the invisible framework within which the visible matter is organized and constrained. Walk through any large collection of galaxy images, the Hubble Deep Field photographs or the images returned by modern wide-field surveys like the Sloan Digital Sky Survey, and the first thing you notice is the variety. Galaxies come in an extraordinary range of shapes and sizes and colors and levels of activity. Some are beautiful pinwheels of blue and white stars with dark lanes of dust tracing their spiral arms. Some are smooth, featureless, golden ellipses. They're like the warm glow of billions of old red and yellow stars. Some are irregular, asymmetric, disturbed, their shapes suggesting recent or ongoing interactions with neighbors. Some are tiny, barely resolved blobs of stars containing only a few million stellar members. Some are enormous, filling enormous volumes of space with their diffuse stellar halos. This variety is not random. It reflects the diverse evolutionary histories of galaxies, the different paths through cosmic time that have led to different present-day structures. The classification of galaxies by morphology, by their visual appearance, was one of the first tasks of extragalactic astronomy, begun in earnest by Edwin Hubble in the 1920s and systematized in what became known as the Hubble sequence or the Hubble tuning fork diagram. At one end of the Hubble sequence are the elliptical galaxies, designated E0 through E7 according to their apparent ellipticity. These are the smooth, featureless, approximately ellipsoidal systems that contain old stars, little gas, and almost no ongoing star formation. They range from nearly circular in projection, the E0 type, to quite elongated, the E7 type, though the apparent ellipticity reflects the three-dimensional shape and the orientation to our line of sight in a complex way. Elliptical galaxies are the most common type in rich galaxy clusters and include the most massive galaxies known. At the other end are the spiral galaxies, divided into normal spirals, designated SA through SD according to how tightly wound their spiral arms are and how prominent their central bulge is, and barred spirals, designated SBA through SBD, which have a bar of stars running through the central region from which the spiral arms emerge. Spiral galaxies like the Milky Way and Andromeda are disk-dominated systems with ongoing star formation, young blue stars in their arms, older yellow and red stars in their bulges, and a diffuse halo of ancient stars. They tend to be found in lower density environments than ellipticals, in the outskirts of clusters and in groups and in isolation. Between the ellipticals and the spirals are the lenticular or S0 galaxies, disc-shaped systems like spirals but lacking the spiral arm structure and with little ongoing star formation, as though they were spirals that had exhausted or lost their gas supply and settled into a quiescent, structurally intermediate state. And then there are the irregulars, the galaxies that do not fit neatly into the elliptical lenticular spiral classification, typically because they have been disturbed by interactions or mergers with other galaxies, their shapes distorted from any regular pattern into the asymmetric, clumpy, often violently star-forming forms characteristic of galactic encounters. This classification, though it was developed before we understood the physical processes driving galaxy evolution, turns out to encode real physical information. Elliptical galaxies are old and dead in the sense of having stopped forming stars. Spiral galaxies are still alive, still forming stars, still processing gas. The morphology of a galaxy is, to a significant degree, a record of its history. We live inside a spiral galaxy, which means we have a perspective on it that no external observer can have, and simultaneously we are denied the perspective that would make its overall structure most apparent. We cannot step outside the Milky Way to photograph it the way we can photograph Andromeda or the Whirlpool Galaxy. We are embedded within it, looking outward from a position about 26,000 light-years from the center, in the disk, between two of the spiral arms, with the entire disk spread around us in every direction in the plane of the sky we call the Milky Way. From our embedded perspective, reconstructing the overall structure of the Milky Way is a bit like trying to map a forest while standing in the middle of it, in fog, unable to fly above it or walk its entire perimeter. We can see the trees nearest to us clearly. We can see their arrangement, their density, their species composition. But the overall pattern of the forest, its shape and extent and the arrangement of its different regions, must be inferred from careful, patient mapping using every tool at our disposal. Those tools have, over the past century, given us an increasingly detailed picture. Radio observations of the 21-centimeter emission of neutral hydrogen, which penetrates the interstellar dust that blocks visible light, have mapped the distribution of gas in the disk across large distances. Infrared observations, which also penetrate dust more effectively than visible light, have revealed the structure of the central region and the distribution of older stars. Observations of star-forming regions, young stellar clusters, and molecular clouds have traced the spiral arms. And the Gaia satellite, launched by the European Space Agency in 2013 and still operating, has measured the positions and motions of more than 1 billion stars with unprecedented precision, giving us the most detailed three-dimensional map of our galactic neighborhood ever constructed. The picture that emerges is of a large barred spiral galaxy. The central region, within a few thousand light-years of the galactic center, contains a dense nuclear disk and a bulge of old stars, structured around a central bar of stars roughly 27,000 light-years long that rotates slowly as a rigid body. The 4 million solar mass black hole, Sagittarius A star, sits at the very center, its presence betrayed by the orbits of stars that pass close to it and by the radio and X-ray emission from matter falling toward it. Outside the central bar, two major spiral arms, the Scutum Centaurus arm and the Perseus arm, emerge from the ends of the bar and wind outward through the disk. Several smaller arm segments and spurs complete the spiral pattern, including the Orion arm, a relatively minor spur in which the solar system is located. The disk as a whole is approximately 100,000 light-years in diameter and perhaps 2,000 light-years thick, though the thickness varies with radius and the disk is not perfectly flat but is warped slightly in the outer regions, bent by the gravitational influence of the Milky Way's satellite galaxies. Beyond the disk, the stellar halo extends to distances of 200,000 light-years or more, populated by ancient globular clusters and old individual stars, relics of the Milky Way's earliest formation history. And beyond even the stellar halo, the dark matter halo extends further still, perhaps to 1,000,000 light-years from the center, its total mass many times greater than all the visible matter combined. This is the galaxy we live in. This is the structure that 4.5 billion years of solar system history has been embedded within. This is the island whose light we see as the Milky Way band on a clear night, the inside view of our own cosmic home. Galaxies are not static objects. They are dynamic systems in a state of continuous, if very slow, change, driven by a combination of internal processes and external influences that together constitute the engine of galactic evolution. The most fundamental internal driver is star formation. As long as a galaxy has a supply of cold gas and the physical conditions that allow that gas to collapse under gravity, it will form new stars. New stars change the galaxy's appearance, adding young, hot, blue stars to the stellar population and contributing to the overall luminosity. They also change the galaxy's chemistry, enriching the interstellar medium with the heavy elements forged in their cores and return to the gas when they die. And the most massive among them die in supernovae that inject energy into the interstellar medium, heating and turbulating the gas, potentially driving galactic winds that blow gas out of the galaxy entirely. Supermassive black holes, present at the centers of virtually all large galaxies, are a second major internal driver. When these black holes are actively accreting matter, swallowing gas and stars from their immediate environment, they release prodigious amounts of energy in the form of radiation and relativistic jets of plasma. This energy, called AGN feedback for active galactic nucleus feedback, can heat and expel the gas from the galaxy's center and potentially from the galaxy as a whole, suppressing star formation and altering the galaxy's evolutionary trajectory in profound ways. External influences are equally important. The environment in which a galaxy lives, whether it is isolated, part of a small group, or embedded in a rich galaxy cluster, shapes its evolution powerfully. Galaxy mergers and interactions, the gravitational encounters between neighboring galaxies, are among the most transformative events in a galaxy's history, triggering starbursts, disturbing disk structures, building up bulges, and ultimately, in major mergers, transforming spiral galaxies into ellipticals. The hot gas that fills galaxy clusters can strip cold gas from galaxies passing through it, a process called ram pressure stripping, removing the fuel for star formation and quenching the galaxy's stellar activity. These drivers, internal and external, operating over billions of years, produce the diversity of galaxy forms and evolutionary states that we observe in the present-day universe. And they produce the systematic changes in the galaxy population over cosmic time, the shift from the irregular, clumpy, vigorously star-forming galaxies of the early universe to the more regular, more quiescent, more structurally mature galaxies of the present day. That is the central subject of our journey tonight. The galaxies are changing. They have always been changing. And they will continue to change, slowly, for as long as the universe has the matter and energy to drive the change. Let us follow them through that change. From the beginning, there was a time when the universe contained no galaxies. This seems like a strange thing to say, given that the universe now contains 2 trillion of them. Given that every direction you look in the night sky, every point of light visible to the naked eye and every smudge and blur and fuzzy patch visible in even a modest telescope, is either a star in our own galaxy or an entire galaxy in its own right, containing hundreds of billions of its own stars. Given that the universe we inhabit appears to be, in the most literal sense, full of galaxies. And yet there was a time, in the first few 100 million years after the Big Bang, when none of this existed. No spirals. No ellipticals. No galaxy clusters. No cosmic web of filaments connecting island after island of light across the dark. Just the smooth, cooling, expanding gas of the post-recombination universe and the invisible, patient, accumulating dark matter halos that were beginning, in the darkness, to lay the foundations for everything that would follow. The birth of galaxies is not a single event. It is a process. A long, complicated, hierarchical, bottom-up process of assembly, in which small things come together to make larger things, in which the first tiny proto-galactic fragments merge and accrete to form dwarf galaxies, and dwarf galaxies merge and accrete to form larger galaxies, and larger galaxies merge to form the full-scale structures we observe today. A process that began in the Dark Ages, hundreds of millions of years after the Big Bang, and that in some sense is still continuing, because galaxies are still merging and still growing in the present-day universe. Tonight we follow that process from its invisible beginning in the dark matter scaffolding of the early universe to the first recognizable galaxies blazing with the light of their newborn stars. Long before the first galaxy formed, before the first star ignited, before there was any light in the universe beyond the fading microwave glow of the cosmic background, the dark matter was building. As we discussed in our journey through the Big Bang, dark matter makes up approximately 27% of the total energy content of the universe, compared to roughly 5% for ordinary baryonic matter, the atoms and molecules and gas that make up everything we can directly observe. Dark matter does not interact with electromagnetic radiation. It does not emit light, absorb light, or scatter light. It responds only to gravity. And this property, which makes dark matter invisible to every telescope ever built, also makes it the universe's most efficient builder of structure in the early universe. In the hot, dense plasma of the early universe, before recombination, the ordinary matter was coupled to the radiation field. The photons and the baryons were locked together in a single photon-baryon fluid, and the radiation pressure of the photons resisted the gravitational collapse of the baryons into denser structures. Every time gravity tried to pull a slightly overdense region of ordinary matter into a tighter, denser clump, the radiation pushed back, creating the acoustic oscillations we discussed earlier. Ordinary matter could not collapse freely. Dark matter had no such impediment. It does not couple to radiation. It has no radiation pressure. It can fall freely into any gravitational well, pulled by any density enhancement, accumulating in structures without the resistance that slows ordinary matter. And so while the ordinary matter oscillated in the photon-baryon fluid, the dark matter was quietly, invisibly, falling into the first halos. The density fluctuations seeded by inflation, those tiny 1 in 100,000 variations in the density of the primordial universe, were the seeds. The slightly overdense regions had slightly stronger gravity. They attracted dark matter from their surroundings. The more dark matter accumulated, the stronger the gravity, the more efficient the attraction. The process was slow at first, imperceptible in any individual moment, but relentless and cumulative. Over hundreds of millions of years, the dark matter assembled itself into halos, clumps of varying sizes distributed through space in a pattern that reflected the original density fluctuations amplified by gravity. The smallest halos formed first. This is a consequence of the physics of the density fluctuations. Small-scale fluctuations have slightly higher amplitude than large-scale ones in the typical inflationary spectrum, and smaller objects collapse earlier at a given density contrast. The first dark matter halos, forming a few 100 million years after the Big Bang, were small, perhaps 1 million times the mass of the Sun, far smaller than the halos that host present-day galaxies. These small halos then merged, hierarchically, into larger and larger structures, assembling the galaxy-scale halos that could host the first proper galaxies. This bottom-up, hierarchical assembly is the foundation of the modern understanding of galaxy formation, called the lambda-CDM model, where lambda refers to the cosmological constant representing dark energy and CDM stands for cold dark matter. In this framework, all large structures grow from the merger of smaller structures, and the dark matter halo is the primary unit of cosmic structure, with the visible galaxy assembling within the halo as ordinary matter falls in and cools. Once the dark matter halos had assembled to sufficient mass, the gravitational wells they created were deep enough to begin capturing and retaining ordinary matter. Hydrogen and helium gas, the product of Big Bang nucleosynthesis, had been drifting through the expanding universe since recombination, cooling gradually, following the density distribution of the dark matter. When a dark matter halo became massive enough, its gravity began to pull this gas in from the surrounding intergalactic medium. The infalling gas did not arrive gently. As it fell into the gravitational well of the dark matter halo, it accelerated, converting the gravitational potential energy of its infall into kinetic energy. When streams of infalling gas collided with each other, or with gas already in the halo, the kinetic energy was converted into heat through shocks. The gas arrived hot, heated to temperatures of millions of degrees by the violence of its collapse, forming a diffuse, hot, puffy atmosphere within the dark matter halo called the hot halo gas or the circumgalactic medium. Hot gas does not immediately form stars. It must first cool. And cooling requires the gas to radiate away its thermal energy, emitting photons that carry the energy away into the surrounding space. The rate at which gas can cool depends on its temperature and density and composition. At the temperatures typical of the hot halo gas, the dominant cooling processes are the emission of X-rays by electrons interacting with ions and the line emission of various atomic and ionic species. These processes are most efficient at particular temperature ranges and at sufficiently high gas densities. In the dense central regions of the dark matter halo, where the gas has fallen to its highest densities, cooling is most efficient. The gas cools, loses pressure support, and sinks further into the center, where it cools more, sinks more, and eventually reaches temperatures low enough to form molecular hydrogen and other molecules. At this point, the gas is cold and dense enough to be gravitationally unstable, and it begins to fragment into smaller clumps that will become the first stars. This process, the cooling and sinking of hot halo gas into a cold, dense central concentration from which stars can form, is called radiative cooling, and it is one of the most fundamental steps in galaxy formation. It is the mechanism by which the diffuse, hot, widespread material of the intergalactic medium is converted into the concentrated, cold, star-forming material of galactic disks and protogalactic fragments. The timescale for this process depends on the mass of the halo and the density of the gas. In the smallest halos, the gas can cool and collapse to form stars relatively quickly after the halo forms. In the most massive halos, the cooling time is longer, and the gas may remain hot and extended for a long time before cooling enough to form a galaxy. This difference in cooling efficiency with halo mass is one reason the universe's first galaxies were small. The small halos that formed first also had the most efficient cooling and produced the first stars, while the massive halos of today's giant galaxies took much longer to assemble their stellar populations. The first recognizable galaxies, the objects we would call galaxies rather than merely protogalactic fragments, began to appear somewhere between 100 and 500 million years after the Big Bang, in the epoch when the first stars were forming and the cosmic dark ages were ending. These first galaxies were nothing like the grand spirals and serene ellipticals of the present-day universe. They were small, irregular, chaotic, and extraordinarily active. They were small because they were the products of the first dark matter halos, which were themselves small. The first galaxies contained perhaps a few million to a few 100 million stars, the stellar populations of what we would today call dwarf galaxies, tiny by the standards of the Milky Way. They were irregular because the processes of gas cooling and star formation in the early universe were turbulent and asymmetric, driven by the chaotic merging of small halos and the violent feedback of the first massive stars and supernovae into the surrounding gas. They were bright for their size because they were forming stars at an extraordinary rate relative to their mass. The gas that had accumulated in these early halos was almost pristine primordial gas, essentially pure hydrogen and helium with only the trace enrichment provided by the first population 3 stars. This gas, despite its compositional simplicity, was being compressed and cooled by the gravitational collapse of the halos, and the result was intense, concentrated bursts of star formation. The young, massive, hot stars being born in these galaxies poured out ultraviolet radiation that ionized the surrounding gas, contributing to the reionization of the universe. The James Webb Space Telescope has now observed galaxies existing less than 300 million years after the Big Bang, and the picture it has revealed has both confirmed and surprised the theoretical expectations. On the confirmation side, the galaxies found at these early times are indeed small, compact, and actively star-forming, consistent with the hierarchical assembly picture. On the surprise side, some of these early galaxies are brighter and more massive than the standard models predicted would exist at such early times. The universe was apparently forming stars and assembling stellar mass more efficiently in its first few 100 million years than the models had suggested. This discrepancy, sometimes called the galaxy formation problem or the early galaxy tension, is one of the most actively discussed issues in current observational cosmology. It may indicate that star formation in the early universe was unusually efficient due to the pristine nature of the gas or the specific structure of the dark matter halos. It may indicate that the initial mass function, the distribution of masses among newly formed stars, was different in the early universe, weighted more heavily toward massive, bright stars. Or it may indicate some incompleteness in the standard model of galaxy formation that will require revision as more Webb data accumulates. Whatever its resolution, the early galaxy tension is a sign that we are learning something genuinely new about the first chapter of galactic evolution. The universe's earliest galaxies are not fully understood. They are a frontier, actively being explored with the most powerful astronomical instruments ever built. The first small galaxies did not remain small. They grew through a combination of two processes that operated simultaneously throughout the history of the universe: the accretion of new gas from the intergalactic medium, and the merging of neighboring galaxies into larger structures. Gas accretion, the continuous inflow of gas from the cosmic web into galaxies, is the more continuous and in some respects the more fundamental of the two. The filaments of the cosmic web, those great thread-like concentrations of dark matter and gas that connect galaxy clusters and groups, act as conduits for the delivery of fresh gas to galaxies. Cold gas streams, flowing along the filaments, can penetrate into the centers of dark matter halos without being heated to the high temperatures of the hot halo gas, feeding star formation directly. This cold mode accretion is thought to be particularly important for the growth of galaxies at early times, when the filaments were denser and the accretion rates were higher. Galaxy mergers are more episodic but more transformative. When two dark matter halos come close enough that their gravitational attraction overcomes the expansion of the universe, they fall toward each other and eventually merge. The galaxies within them, carried along by the merging halos, interact gravitationally, their stellar populations and gas clouds disturbed by the tidal forces of the encounter, before eventually merging into a single, larger galaxy. The merger history of any individual galaxy is complex and branching. The Milky Way, for example, grew to its current size through the accretion of dozens or hundreds of smaller satellite galaxies and protogalactic fragments over its 13-billion-year history. The ancient stellar halo of the Milky Way, the diffuse population of old stars and globular clusters that surrounds the disk, is largely composed of the stellar debris from these past mergers, stars that were stripped from their original galaxies by tidal forces and scattered into the halo during the merging process. The Gaia satellite has been instrumental in revealing the Milky Way's merger history by measuring the positions and three-dimensional velocities of large numbers of halo stars with unprecedented precision. Stars from the same accreted satellite galaxy share similar orbital properties, forming coherent kinematic structures in the halo even billions of years after the merger that originally placed them there. Gaia has identified several major past merger events in the Milky Way's history, including one called Gaia Enceladus or Gaia Sausage, a merger with a galaxy of roughly a quarter of the Milky Way's current mass that occurred approximately 8 to 10 billion years ago and contributed a large fraction of the Milky Way's inner halo stellar population. This picture of galaxies growing through the hierarchical merging of smaller structures is one of the most thoroughly tested and most robustly confirmed predictions of the Lambda-CDM model of cosmology. The distribution of satellite galaxies around large galaxies, the properties of galaxy halos, the correlation between galaxy mass and the number of globular clusters they contain, all of these observations are consistent with a universe in which structure grows hierarchically, bottom up, from the merger and accretion of smaller units. The birth of galaxies was not a uniform, steady process spread evenly across cosmic time. It had a peak, a moment in the universe's history when galaxies were forming stars most vigorously, when the universe as a whole was converting gas into stars at the highest rate it has ever achieved, when the cosmic star formation rate density, the total mass of new stars being formed per year per unit volume of the universe, reached its maximum. That peak occurred approximately 2 to 3 billion years after the Big Bang, when the universe was roughly 2 to 3 billion years old, in the redshift range that astronomers call cosmic noon. At cosmic noon, the average galaxy in the universe was forming stars at a rate several to 10 times higher than typical present-day star-forming galaxies. The universe was alive with star formation in a way it has never been since and will never be again. Infrared and radio observations of this epoch reveal a universe blazing with the thermal emission of dust heated by the intense ultraviolet radiation of young massive stars, a landscape of furiously star-forming galaxies scattered across the cosmic web. The peak of star formation at cosmic noon was the result of several factors converging. By 2 to 3 billion years after the Big Bang, the dark matter halos had grown massive enough to host substantial galaxies. The gas that had been cooling and accumulating in these halos over the preceding billion years was available for star formation. And the rate of galaxy mergers, which were more frequent in the denser early universe, was triggering additional bursts of star formation by compressing gas and driving it into the central regions of merging systems. Since cosmic noon, the overall star formation rate in the universe has declined. Not dramatically, not all at once, but steadily, by roughly an order of magnitude from the peak to the present day. The universe is forming stars today at about 1/10 the rate it was at cosmic noon. The gas supplies in many galaxies have been depleted by the conversion of gas into stars over billions of years. The rate of galaxy mergers has declined as the universe has expanded and the density of galaxies has decreased. And the process of quenching, which we will explore in detail in a later chapter, has shut down star formation in a significant fraction of the galaxy population entirely. The universe, in its stellar activity, is declining from a peak it reached in its youth. We live in the middle of a long, slow exhale, a cosmic afternoon following the brilliant morning of cosmic noon, in which the stars are still forming but at a fraction of the rate they once did, and the overall stellar content of the universe is growing only slowly because the formation of new stars is nearly balanced by the deaths of old ones. The galaxies we see around us today are the survivors of that brilliant, violent, chaotic early epoch. They carry in their stellar populations, their chemical compositions, and their structural properties the record of how they formed and grew during the universe's most active period. Reading that record, understanding what it tells us about the birth and early evolution of galaxies, is one of the central tasks of modern extragalactic astronomy. And we are getting better at it. With every new telescope, every new survey, every new computational simulation, the picture becomes richer and more detailed. The birth of galaxies is no longer the mystery it was a generation ago. It is a story we are learning to tell with increasing confidence and increasing precision. A story that begins in the dark, with invisible matter falling into invisible wells, and ends with the blazing, chaotic, magnificent light of the universe's first stellar nurseries. It is, by any measure, one of the great stories of science. And we are still in the middle of telling it. Of all the shapes in the universe, None is more immediately recognizable, none more instinctively beautiful, none more deeply associated in the popular imagination with the grandeur of the cosmos than the spiral galaxy. The pinwheel of stars and gas and dust curving outward from a bright central hub, the trailing arms traced in blue-white young stars and dark lanes of absorbing dust, the whole structure rotating with a stately, almost hypnotic elegance. It is the shape that appears on 1,000 astronomy book covers and 1,000,000 screensavers. It is the shape that says galaxy to anyone who has ever looked up. And it should not exist. Not in the way it appears to exist, anyway. The spiral arms of a galaxy look like permanent features, like the spokes of a wheel or the blades of a pinwheel, rotating rigidly along with the stars that compose them. But they are not. They cannot be. The physics of orbital mechanics in a galaxy makes rigid spiral arms impossible, and has done so for a long time. The puzzle of how spiral arms can exist at all, given this impossibility, occupied astronomers for decades and produced one of the most elegant and surprising insights in the history of astrophysics. The answer, when it finally came, revealed spiral arms to be something far more interesting than permanent structures. They are waves. Density waves. Patterns of compression moving through the stellar disk of a galaxy the way a sound wave moves through air, carrying no permanent material with it, only a transient crowding of whatever material happens to be passing through the pattern at any given moment. The stars you see in a spiral arm tonight are not the same stars that were in that arm 1,000,000,000 years ago. In 1,000,000,000 years, they will be somewhere else entirely. The arm itself will still be there, marked by different stars, carrying a different portion of the galaxy's gas, but persistent, beautiful, and structurally recognizable, a wave that moves through the galaxy's disk on timescales of hundreds of millions of years. Let us understand this properly, because it is one of the most quietly astonishing things in all of astronomy. The problem begins with a simple observation about how galaxies rotate. Unlike the solar system, where the planets obey Kepler's laws and the inner planets move faster than the outer ones, a spiral galaxy does not rotate like a rigid body or like a solar system. The rotation curve of a spiral galaxy, the graph of orbital velocity versus distance from the center, is not the declining curve you would expect if most of the mass were concentrated at the center. It is approximately flat. Stars at different distances from the galactic center orbit at roughly the same speed, or sometimes the outer stars orbit slightly faster than expected. This flat rotation curve is itself one of the most important pieces of evidence for dark matter. It indicates that the mass distribution in a galaxy extends far beyond the visible stars and gas, into the dark matter halo, keeping the orbital speeds high even at large radii. But the flatness of the rotation curve has another consequence that is immediately relevant to the question of spiral arms. If stars at different distances from the center orbit at the same speed in kilometers per second, then stars at different distances complete their orbits in very different times. A star close to the center has a small orbit to complete at a given speed and completes it quickly. A star far from the center has a large orbit to complete at the same speed and takes much longer. The inner stars orbit faster in the angular sense, completing more revolutions per unit time than the outer stars. This differential rotation means that any feature drawn across the disk of a galaxy, any radial line or arm connecting stars at different distances from the center, will be shared by the differential rotation. The inner end will race ahead of the outer end. A straight radial feature will quickly become curved, trailing behind the faster rotating inner regions. And if the arm were a permanent, material feature, composed always of the same stars, the shearing would be relentless. After a few galactic rotations, the arm would be wound so tightly around the galaxy that it would be invisible as a distinct structure, indistinguishable from the general background of stars in the disk. This is called the winding problem, and it was recognized as a serious difficulty for any model of spiral galaxies as soon as astronomers began to understand how galaxies rotate. A galaxy like the Milky Way has completed approximately 18 to 20 orbits since it formed. If the spiral arms were material features that had been present from near the beginning, they would have been wound into invisibility long ago. And yet they are there. And yet every spiral galaxy we observe has clearly defined, opened, beautiful spiral arms that look nothing like a wound-up tangle. Something is maintaining the arms. Something is preventing the winding. For decades, this something was mysterious. The solution to the winding problem was developed in the 1960s primarily by the Chinese-American astrophysicists Chiao Lin and Frank Xu, working at the Massachusetts Institute of Technology. Their insight was to stop thinking of spiral arms as material structures, collections of stars and gas traveling together, and start thinking of them as patterns, density waves propagating through the stellar disk. The analogy that is most often used, and that I think genuinely illuminates the concept, is traffic on a highway. Imagine driving on a highway and encountering a slow-moving section, perhaps because of road construction or an accident, where cars have slowed and bunched together. From the air, this slow section looks like a dense region of cars, a visible concentration moving down the highway at the speed of the obstruction. As individual cars approach the slow section, they slow down and join the density enhancement. As they pass through and the obstruction is behind them, they speed up and drive away. The cars in the dense section are constantly changing, new cars arriving and old ones departing, but the dense section itself persists as a pattern, traveling at a different speed from the individual cars that pass through it. Spiral arms work in an analogous way. The density wave is a region of slightly enhanced gravitational potential that rotates around the galaxy at a speed called the pattern speed, which is generally different from the speed at which the individual stars orbit. Stars moving through the disk encounter the density wave, slow slightly as they pass through the region of enhanced gravity, spend more time in it, and then speed up again as they exit on the other side. The result is that at any given moment, the density wave region contains more stars than the surrounding disk, simply because stars spend more time there. The arm appears as a region of enhanced stellar density, marked by the bright young stars and luminous gas clouds that form within it, even though the individual stars are constantly flowing through it rather than residing permanently within it. The gas in the disk is particularly sensitive to the density wave. When diffuse interstellar gas enters the density wave from the leading edge, it encounters a mild shock, a compression that increases its density dramatically. This compression is often sufficient to push the gas over the threshold for gravitational collapse and star formation. And so the leading edges of spiral arms are marked by dense molecular clouds and active star formation, producing the young, hot, blue stars whose brilliant light traces the arm's outline. The dark dust lanes visible on the leading edges of spiral arms in nearby galaxies are the compressed gas and dust entering the shock. The brilliant blue star clusters on the trailing edge are the newly formed stars that have just emerged from their birth clouds. The density wave is self-sustaining, at least in principle. The enhanced star formation it triggers produces massive stars that die in supernovae, injecting energy into the interstellar medium in ways that can help maintain the density enhancement. The arms are not permanent in the sense of being composed of the same material, but they are persistent in the sense of being maintained by a stable pattern that continues as long as the conditions that generate it persist. Density wave theory elegantly solves the winding problem and explains many of the observed properties of spiral arms. But it does not fully specify what generates and maintains the density wave in the first place. The theory describes the wave but does not entirely explain its origin. And the more carefully astronomers have studied spiral galaxies, the more it has become clear that spiral structure is not a single phenomenon with a single explanation. It is a family of phenomena, with multiple possible origins and multiple modes of expression. In grand design spirals, the most visually spectacular type, with two well-defined, symmetric arms extending continuously from the central regions to the outer disk, the spiral pattern is often driven by a tidal interaction with a neighboring galaxy. The gravitational influence of a passing or orbiting companion galaxy can excite a two-armed density wave in the disk, imprinting a coherent, symmetric spiral pattern that persists for several galactic rotations after the tidal encounter. The Whirlpool Galaxy, Messier 51, is a beautiful example. Its grand two-armed spiral is thought to be largely driven by the gravitational interaction with its smaller companion galaxy, NGC 5195, which is visible in images as a small bright knot apparently connected to one of the whirlpool's arms. In flocculent spirals, the Messier, more fragmented type with many short, patchy arm segments rather than two clean grand arms, the spiral structure is thought to arise more locally, from the self-propagating nature of star formation. A massive star forms, lives briefly, and dies in a supernova that compresses the surrounding gas, triggering the formation of new stars nearby. Those new stars form their own massive members that die in supernovae that trigger still more star formation in adjacent regions. The result is a chain reaction of star formation that, shaped by the differential rotation of the disk, produces short, curved arm segments with a roughly spiral appearance. This mode of spiral structure does not require a density wave in the classical sense. It emerges from the local, stochastic processes of star formation and feedback. Many real spiral galaxies, including the Milky Way, appear to have elements of both grand design and flocculent structure, with some global spiral pattern, possibly excited by the bar or by past interactions with satellite galaxies, superimposed on a background of more locally driven star formation activity. The Milky Way's spiral structure is particularly difficult to map from our embedded perspective, and its precise number and geometry of arms remain a subject of active debate and ongoing observational work. Many spiral galaxies, estimated at between 40 and 70% of all spirals including our own Milky Way, have not just spiral arms but a bar. A bar is a linear, rectangular or diamond-shaped concentration of stars running through the central region of the galaxy, from which the spiral arms emerge at or near the bar's ends. In images of barred spirals, the bar is unmistakable, a bright, elongated central structure that bisects the galaxy, with the spiral arms curving away from its tips like the curved blades of a particular type of pinwheel. A galactic bar is not a static structure any more than the spiral arms are. It is a dynamical feature, maintained by the coherent orbital motion of the stars within it. The stars in a bar are not traveling parallel to the bar's long axis. They are moving in elongated orbits, called X1 orbits, whose long axes are aligned with the bar. The collective effect of many stars in these aligned orbits is to produce the bar's elongated shape, which then reinforces the orbital alignment through its own gravity, creating a self-sustaining structure. The bar is not merely a passive feature. It is an active engine of galactic evolution. As the bar rotates, it exerts gravitational torques on the gas in the disk, creating a pattern of spiral density waves at its ends and driving gas inward along the bar toward the galactic center. This inward gas flow can fuel star formation in the central regions, building up the central mass concentration and potentially feeding the supermassive black hole at the galaxy's center. Bars are thought to be one of the primary mechanisms for transporting gas from the outer disk to the central regions of galaxies, playing a crucial role in the evolution of the central bulge and the growth of the central black hole. The Milky Way's bar was confirmed observationally in the 1990s through infrared observations that penetrated the dust obscuring the galactic center. Its length is estimated at approximately 27,000 light-years, extending roughly 13,000 light-years on either side of the galactic center. The bar rotates with a pattern speed that is currently estimated at about 35 to 40 kilometers per second per kiloparsec, slower than the orbital speed of stars in the disk at the Sun's distance from the center. The Sun is currently well outside the bar's corotation radius, the distance at which stars orbit at the same angular speed as the bar, and the influence of the bar on the solar system's orbit is relatively modest. But the bar's influence on the Milky Way's evolution has been profound. Over billions of years, it has been driving gas inward, building up the central bulge, shaping the distribution of stellar populations in the inner galaxy, and mediating the flow of material to the supermassive black hole. The bar is the Milky Way's quiet engine, working on timescales of hundreds of millions of years to reshape the galaxy from the inside out. Spiral galaxies do not maintain their spiral structure forever. As galaxies evolve, the conditions that support spiral arms can change, and the spiral structure can be disrupted, weakened, or transformed into something else entirely. Understanding how and when spiral galaxies lose their spiral structure is one of the key questions connecting the morphological evolution of the galaxy population to the physical processes of galaxy evolution. The most dramatic way a spiral galaxy can lose its structure is through a major merger with another galaxy of comparable mass. When two spiral galaxies collide and merge, the thin, dynamically cold disks of both galaxies are destroyed by the tidal forces and gravitational churning of the merger. The stars that were ordered in a flat rotating disk are scattered into three-dimensional, chaotic orbits by the violent gravitational perturbations of the encounter. The gas is driven inward in a massive starburst, consumed in a brief but intense episode of star formation. And the remnant of the merger, after the violence subsides and gravity draws the material into a new equilibrium over hundreds of millions of years, is typically a smooth, featureless elliptical galaxy with no disk and no spiral arms. This transformation, from spiral to elliptical through merger, is one of the most important pathways in the morphological evolution of the galaxy population. It is thought to be responsible for the large elliptical galaxies found at the centers of galaxy clusters, which have grown to their enormous sizes through repeated mergers with smaller galaxies over billions of years. The observation that elliptical galaxies are more common in dense cluster environments, while spirals are more common in the lower density field, is consistent with the idea that the higher merger rates in clusters have converted spirals into ellipticals more efficiently there. More gentle processes can also affect spiral structure without destroying it entirely. A minor merger, the accretion of a much smaller satellite galaxy, can heat the stellar disk, thickening it and reducing the prominence of the spiral arms without completely disrupting the galaxy. Ram pressure stripping, the removal of cold gas from a galaxy as it moves through the hot intracluster medium, can deplete the gas supply that fuels the star formation in spiral arms, causing the arms to fade as the bright young stars that mark them die and are not replaced. And the bar itself can contribute to the gradual transformation of spiral structure. As a bar drives gas inward and builds up the central mass concentration, the increasing central mass changes the orbital structure of the disk in ways that can affect the nature and persistence of the spiral arms. The bar can also gradually slow its own rotation through angular momentum exchange with the dark matter halo in the outer disk, changing its dynamical influence over time. The spiral arm you are imagining right now, if you close your eyes and picture a galaxy, is a beautiful and temporary thing. A wave of compression and star formation, marking its passage through the disk with the brilliant blue light of young stars and the warm glow of heated gas. Rotating with a patience measured in tens of millions of years. Carrying within it, at any given moment, only the stars and gas that happen to be passing through it, none of them aware of their brief residency in one of the universe's most celebrated structures. The spiral is a song that the galaxy sings to itself. A slow, patient, rotating song. And like all songs, it will eventually end. But tonight, in this galaxy and in 2 trillion others scattered across the observable universe, the song is still playing. At the center of almost every large galaxy in the universe, something extraordinary is hiding. Not hiding in the sense of being absent or invisible, though it is both of those things in ordinary light. Hiding in the sense of being present but not immediately apparent, embedded in the dense, bright central regions of the galaxy, detectable only through indirect evidence, through the orbits of stars moving too fast around something too massive to be any ordinary concentration of matter, through the occasional brilliant outburst of radiation when matter falls into it, through the tight, narrow jets of plasma it sometimes launches at nearly the speed of light deep into the surrounding space. A supermassive black hole, containing millions to billions of times the mass of the Sun, compressed into a volume far smaller than the solar system, surrounded by an event horizon from within which nothing can escape. At the center of the Milky Way, Sagittarius A star, 4 million solar masses. At the center of the Andromeda Galaxy, 100 million solar masses. At the center of the giant elliptical galaxy M87, 6.5 billion solar masses. At the center of a quasar in the distant universe, sometimes tens of billions of solar masses, actively accreting matter at a rate that makes the surrounding region the most luminous object in the observable universe. For most of the 20th century, supermassive black holes were thought of as exotic but essentially passive objects, curiosities at galactic centers that had little to do with the broader structure and evolution of their host galaxies. The galaxy was the important thing. The black hole was an incidental byproduct of galactic evolution, a massive remnant of the processes that had built up the central regions, interesting in its own right but not causally important for the galaxy's overall development. That view has been completely overturned. Over the past 30 years, a combination of observational discoveries and theoretical insights have revealed that supermassive black holes and their host galaxies are deeply, intimately, causally connected. That the black hole does not merely sit passively at the galaxy's center but actively participates in the galaxy's evolution, sometimes dramatically, sometimes subtly, sometimes in ways that determine whether the galaxy continues to form stars or goes permanently quiet. The monster at the center of the galaxy is not a passive tenant. It is, in a very real sense, one of the landlords. The first strong evidence that supermassive black holes and their host galaxies are fundamentally connected came not from any observation of the black holes themselves but from a remarkable correlation discovered in the late 1990s between the mass of a galaxy's central black hole and a property of the galaxy's bulge called the velocity dispersion. The velocity dispersion of a galaxy's bulge is a measure of how fast the stars in the bulge are moving relative to each other. It is not the ordered rotational velocity of the disk, but the random, thermal-like spread of stellar velocities around the mean, the degree to which the stellar orbits in the bulge are chaotic rather than organized. A higher velocity dispersion means the stars are moving faster relative to each other, which in turn means the bulge is deeper in the gravitational potential, which generally means it is more massive. The m-sigma relation, named for the black hole mass m and the velocity dispersion sigma, states that the mass of the central black hole is tightly correlated with the velocity dispersion of the surrounding bulge. More precisely, the black hole mass scales approximately as the fifth power of the velocity dispersion. Double the velocity dispersion and the black hole mass increases by a factor of approximately 32. This is a steep relationship, and it is tight, meaning that knowing the velocity dispersion of a galaxy's bulge allows you to predict the mass of its central black hole with reasonable accuracy, and vice versa. This correlation was immediately recognized as remarkable for several reasons. First, the black hole is tiny compared to the bulge. The event horizon of even a supermassive black hole is measured in light days to light years, while the bulge it sits within extends for thousands of light years. The black hole contains perhaps a fraction of a percent of the bulge's total mass. They seem to be operating at completely different scales. And yet their properties are correlated with a precision that suggests they are not independent. Second, the correlation holds across an enormous range of galaxy masses and black hole masses. From small galaxies with relatively modest black holes to the most massive ellipticals with the most extreme supermassive black holes, the m-sigma relation holds. It is one of the tightest scaling relations in all of extragalactic astronomy. The tightness and universality of this correlation strongly suggest a causal relationship, a co-evolutionary connection in which the growth of the black hole and the growth of the bulge are regulated by the same physical process, or in which the black hole directly influences the evolution of the bulge, or vice versa. Disentangling the causal direction of this relationship has been one of the central puzzles of galaxy evolution research for the past quarter century. A supermassive black hole sitting quietly at a galactic center, accreting nothing or accreting at a very low rate, is invisible. It gives no sign of its presence except through the gravitational influence on nearby stars and gas. But when a supermassive black hole is actively accreting material at a high rate, when substantial quantities of gas are falling toward it and forming the hot, luminous accretion disk that surrounds the event horizon, it becomes the most luminous object in the universe. It wakes up. And when it wakes, it announces itself across cosmic distances. Active galactic nuclei, or AGN, is the umbrella term for the diverse family of phenomena associated with actively accreting supermassive black holes. Quasars, the most extreme and most distant members of the family, are black holes accreting at rates close to their theoretical maximum, pouring out energy at luminosities that can exceed the combined light of hundreds of billions of stars. Safer galaxies are nearby, less extreme AGN in which the nuclear activity is evident but does not overwhelm the light of the host galaxy. Radio galaxies and blazars are AGN characterized by powerful relativistic jets of plasma launched perpendicular to the accretion disk, extending from the nuclear region to distances of hundreds of thousands of light years and beyond. And low luminosity AGN, including the relatively quiescent active nucleus of our own Milky Way, are black holes accreting at very low rates, their activity detectable only by sensitive observations at radio and X-ray wavelengths. The energy source of AGN is gravity. As matter falls toward the black hole and spirals inward through the accretion disk, it loses gravitational potential energy, and that energy is released as radiation. The efficiency of this process, the fraction of the rest mass energy of the infalling matter that is converted to radiation, is extraordinarily high by the standards of any other energy source in the universe. Nuclear fusion in stellar cores converts approximately 0.7% of rest mass to energy. Accretion onto a spinning black hole can convert up to approximately 42% of the rest mass of the infalling matter to energy. Per unit mass of fuel consumed, an AGN is orders of magnitude more energetic than any star. The total energy released by a supermassive black hole over its lifetime of active accretion is staggering. A black hole of 1 billion solar masses, assembled primarily through accretion with a radiative efficiency of 10%, releases an energy of approximately 10 to the 62 ergs over the course of its growth. This is comparable to, or in many cases greater than, the total binding energy of the host galaxy's stars. The AGN has the energy, in principle, to unbind the galaxy's entire gas supply, to heat or expel every atom of the interstellar medium, to permanently shut down star formation. Whether and how this energy actually couples to the galaxy's gas, how it is transferred from the scales of the black hole's immediate environment to the scales of the galaxy and beyond, is the central question of AGN feedback, and it is one of the most active and contested areas of current research in galaxy evolution. The term feedback in astrophysics refers to the process by which the energy or material output of one process affects the conditions that drive that process, or affects other processes operating in the same system. Stellar feedback is the influence of supernovae and radiation from massive stars on the surrounding interstellar medium. AGN feedback is the influence of the energy output of an active galactic nucleus on the gas, star formation, and broader evolution of the host galaxy. AGN feedback is thought to operate in two broad modes, called quasar mode feedback and radio mode feedback, which correspond to different accretion states of the black hole and which affect the host galaxy in different ways. Quasar mode feedback, also called radiative mode feedback, operates when the black hole is accreting at a high rate and the AGN luminosity is high. In this mode, the intense radiation from the accretion disk and the powerful winds that are driven off the disk's surface by radiation pressure interact directly with the gas in the host galaxy. The winds, traveling at thousands of kilometers per second, can sweep up and accelerate the galaxy's interstellar medium, driving powerful outflows that carry gas out of the galactic disk and potentially out of the galaxy entirely. The radiation heats and ionizes the gas, preventing it from cooling efficiently. Both effects reduce the gas available for star formation and can, in extreme cases, quench star formation across the galaxy on relatively short timescales of tens of millions of years. Radio mode feedback, also called kinetic mode feedback, operates when the black hole is accreting at a low rate but is launching powerful relativistic jets. The jets, directed perpendicular to the accretion disk, carry enormous mechanical energy outward into the surrounding medium. When these jets encounter the hot gas that fills galaxy clusters, they heat it, inflating enormous cavities or bubbles in the X-ray emitting gas that are visible in deep X-ray images of galaxy clusters as dark voids surrounded by brighter rims. By heating the intracluster medium and preventing it from cooling and falling back into the galaxy, jet-driven feedback can maintain a quasi-steady state in which the gas supply for star formation is perpetually heated faster than it cools, keeping the galaxy permanently quenched even in the absence of a strong radiative AGN. The observational evidence for AGN feedback is now extensive and compelling. Galactic-scale outflows of gas with velocities of hundreds to thousands of kilometers per second are observed in many AGN host galaxies, with outflow rates in some cases exceeding the star formation rates by large factors, clearly capable of removing substantial quantities of gas from the galaxy over timescales of hundreds of millions of years. The X-ray cavities in galaxy clusters, inflated by AGN jets, are observed in essentially every nearby cool core cluster and contain enough mechanical energy to offset the cooling of the cluster gas. And statistical studies of the galaxy population show clear evidence that AGN activity is correlated with the suppression of star formation, with the transition of galaxies from the blue, star-forming sequence to the red, quiescent sequence. The monster at the galactic center is not merely an object of fascination for its extreme physics. It is a regulatory mechanism. A thermostat. It regulates the temperature of the gas in and around its host galaxy, moderating the star formation rate, shaping the galaxy's stellar population, and ultimately determining whether the galaxy continues to grow and evolve or settles into quiescence. The M-sigma relation, that tight correlation between black hole mass and bulge velocity dispersion, is probably the imprint of this regulatory process. The black hole grows until its feedback energy is sufficient to expel the gas that was feeding it and to quench the star formation that was building the bulge, at which point both growth processes stop, leaving the tight correlation between their final states. Of all the manifestations of AGN activity, none is more extreme or more cosmologically important than the quasar. Short for quasi-stellar radio source, a name inherited from the earliest radio surveys that found point-like radio sources that turned out to be enormously distant and luminous objects rather than the ordinary stars their compact appearance suggested. Quasars are AGN in their most active state, black holes accreting near their maximum rate and releasing energy at luminosities that can reach 10 to the 48 ergs per second. To understand what this luminosity means, Consider that the Sun's luminosity is approximately 4 times 10 to the 33 ergs per second. A luminous quasar outshines the Sun by a factor of roughly 10 to the 15, or 1,000 trillion. It outshines the entire Milky Way, with its hundreds of billions of stars, by a factor of roughly 10 to the 3 to 10 to the 4. A single black hole, in its most active phase, can outshine a galaxy of hundreds of billions of stars by a factor of thousands. The most luminous quasars are the most luminous persistent objects in the observable universe. Quasars are predominantly a phenomenon of the early universe. The quasar luminosity function, which describes the number density of quasars as a function of luminosity and redshift, peaks at a redshift of approximately 2 to 3, corresponding to the epoch of cosmic noon that we discussed earlier. This is the epoch when galaxies were forming stars most vigorously and when the most rapid growth of supermassive black holes was occurring. The two peaks coincide because both star formation and black hole growth require the same fuel, cold gas. When the universe was richest in cold gas, available in large quantities in the rapidly merging and accreting protogalactic systems of the early universe, both processes were at their most vigorous. Since that peak, the quasar population has declined dramatically. The most luminous quasars are rare in the present-day universe, their fuel supplies depleted by the very feedback processes they drive and by the general decline in cold gas availability as the universe ages and expands. Most present-day supermassive black holes, including Sagittarius A star at the center of the Milky Way, are in a low accretion, low luminosity state. Their quasar phase a distant memory encoded in the tight correlation between their mass and the properties of their host galaxy's bulge. What we see when we observe distant quasars is the past. The light from a quasar at redshift 3 left its source approximately 11 billion years ago, when the universe was roughly 2.5 billion years old. We are not seeing active quasars in the present-day universe at those luminosities. We are seeing the past. The quasar phase of massive black hole growth was a phenomenon of the universe's youth, a brilliant, violent, prodigiously energetic chapter in the history of galaxy formation that has now largely passed, leaving behind the massive, quiescent, gas-poor elliptical galaxies whose enormous central black holes carry the memory of that early activity. The monster fed voraciously in the universe's childhood. It grew enormous on the abundant gas of the early universe, pouring out energy that shaped and ultimately quenched the galaxies it inhabited. And then, its fuel depleted and its feedback having cleared the immediate environment, it fell quiet. It is still there, at the center of every large galaxy, waiting in the dark. Occasionally stirred by a new infusion of gas from a merger or a tidal disruption event, briefly active again for a few million years before settling back into quiescence. Sagittarius A star, the 4 million solar mass black hole at the center of our galaxy, is in one of these quiet phases. It is currently accreting at a rate many orders of magnitude below its maximum, emitting only a faint flicker of radio and X-ray radiation that would be invisible to naked eye observers even if they could somehow stand at the galactic center. But approximately 4 million years ago, in what astronomers call the Seyfert flare or the Milky Way AGN event, Sagittarius A star was apparently much more active, its luminosity millions of times higher than today, its radiation ionizing gas across tens of thousands of light years. The evidence for this past activity is written in the glowing clouds of ionized gas above and below the galactic disk, the Fermi bubbles discovered by the Fermi Gamma Ray Space Telescope in 2010, enormous structures extending roughly 25,000 light-years above and below the galactic plane, filled with hot plasma and cosmic rays that were apparently driven out by the past activity of Sagittarius A star. The monster in our own galaxy center has not always been quiet. It was, in its distant past, something like a quasar. The memory of that activity is still glowing, faintly, in the bubbles it left behind. The center of our galaxy carries the scars of its own violent history. Quietly, in the dark, waiting. The universe is not a peaceful place. At the human scale, the night sky presents an image of serene stillness, the stars fixed in their constellations, the galaxies hanging motionless in the dark like luminous clouds, the whole arrangement suggesting a cosmos of eternal, unchanging calm. But the calm is an illusion of timescale. On the timescale at which galaxies operate, on the scale of hundreds of millions and billions of years, the universe is a place of constant, dramatic, occasionally catastrophic interaction. Galaxies collide. They tear each other apart. They consume each other. They merge, slowly and violently, into new structures bearing little resemblance to the originals. Galaxy mergers are among the most consequential events in the history of any galaxy that experiences them. They can trigger the most intense starbursts in the universe, episodes of star formation so vigorous that a galaxy consumes in tens of millions of years the gas it would otherwise have used over billions. They can awaken dormant supermassive black holes, driving gas into the central regions that ignites quasar activity. They can destroy the thin, ordered disk structures of spiral galaxies, scattering their stars into the chaotic, featureless distributions of elliptical galaxies. They can build the most massive galaxies in the universe, the enormous elliptical giants at the centers of galaxy clusters, through the accumulated debris of billions of years of merging. And they happen slowly enough that, for any individual star caught in the process, nothing dramatic is occurring at any given moment. The merger of two large galaxies takes hundreds of millions of years from first approach to final coalescence. A star in one of the merging galaxies experiences the gravitational perturbations of the other galaxy as a gradual change in its orbital parameters, nudged this way and that over millions of years, its path altered but never subjected to any sudden violence. The drama is in the aggregate, in the collective effect of billions of gravitational nudges on billions of stars over hundreds of millions of years, visible only to observers capable of watching the whole process unfold across geological timescales. Tonight we watch it unfold. A galaxy merger begins long before the galaxies actually touch. It begins when the gravitational attraction between two galaxy halos, each embedded in its dark matter cocoon, overcomes the expansion of the universe that would otherwise carry them apart. The dark matter halos of neighboring galaxies are vastly larger than the visible galaxies they contain. The Milky Way's dark matter halo extends to perhaps 1 million light-years from the galactic center, roughly 10 times the diameter of the visible disk. The dark matter halos of two neighboring galaxies in a loose group can already be in contact, overlapping at their edges, even when the visible galaxies themselves are separated by millions of light-years and appear to be quite separate systems. As the halos begin to overlap and interact, They exert gravitational dynamical friction on each other. Dynamical friction is the process by which a massive object moving through a sea of smaller objects, or through a smooth mass distribution, experiences a drag force because its gravity attracts the surrounding material into a slight overdensity behind it, and the gravitational pull of that overdensity slows the object's motion. In a galaxy merger, the two dark matter halos exert dynamical friction on each other as they interpenetrate, transferring orbital energy from the relative motion of the two halos into the internal random motions of their constituent particles. The orbit of the two galaxies around each other decays. They lose energy and angular momentum. They fall closer together. This orbital decay is slow. The initial approach of two merging galaxies, from their first gravitational interaction to their first close passage, can take billions of years. The Milky Way and the Andromeda Galaxy are currently approaching each other at approximately 110 kilometers per second, a speed that sounds fast by any ordinary measure, but that, given the distance of approximately 2.5 million light-years between them, translates to a first close approach approximately 4 billion years from now. 4 billion years. That is the current phase of the Milky Way-Andromeda merger. The approach. The long, patient falling together of two islands that have been drifting in their mutual gravity well since they formed, whose dark matter halos have been subtly interacting for billions of years already, and which are now, on the cosmic timescale, beginning the final stages of an encounter that will transform both of them beyond recognition. When two galaxies make their first close passage, sweeping past each other at speeds of hundreds of kilometers per second, the gravitational interaction between them produces the most visually spectacular features of galaxy mergers, the tidal tails and bridges that extend from the interacting systems like luminous streamers, sometimes stretching for hundreds of thousands of light years into the surrounding space. Tidal tails form through the differential gravitational force, the tidal force, exerted by one galaxy on different parts of the other. Stars on the side of a galaxy closest to its companion feel a stronger gravitational pull toward the companion than stars at the galaxy's center, and stars on the far side feel a weaker pull. This differential force stretches the galaxy along the line connecting it to its companion, drawing out tidal tails from both the near and far sides. The stars pulled toward the companion form a bridge connecting the two galaxies. The stars pulled away from the companion on the far side form a tail extending in the opposite direction. The antennae galaxies, NGC 4038 and NGC 4039, are perhaps the most famous example of an ongoing galaxy merger in the nearby universe. Approximately 45 million light-years away, the two galaxies are currently in their first close passage, their disks overlapping and their tidal tails extending for hundreds of thousands of light-years in two long, curved streamers that give the system its name. Within the overlap region where the two disks are colliding, the compressed gas has triggered one of the most intense starbursts in the local universe, producing thousands of massive young star clusters that blaze with blue-white light in the infrared and visible images returned by the Hubble Space Telescope and subsequently by James Webb. The tidal tails of merging galaxies are not merely visual spectacles. They are reservoirs of stars and gas stripped from the merging galaxies and scattered into the surrounding space. Some of this material will eventually fall back into the merger remnant as the orbit decays and the galaxies coalesce. Some will be dispersed into the intergalactic medium, contributing to the diffuse stellar halos and intracluster light that surrounds galaxy groups and clusters. And within the tidal tails themselves, the compressed gas can form new stars and even new dwarf galaxies, small self-gravitating systems born from the debris of the collision, called tidal dwarf galaxies. The stellar streams that surround the Milky Way today are the tidal tails and stripped stellar debris of past mergers, the ghosts of galaxies that were absorbed into the Milky Way billions of years ago and have not yet fully mixed into the general stellar background. The Sagittarius Stream, a long arc of stars stretching almost entirely around the sky, is the tidal debris of the Sagittarius Dwarf Galaxy, a small satellite galaxy that has been orbiting the Milky Way and being gradually disrupted by tidal forces for at least several billion years. With each orbit, the Sagittarius Dwarf loses more stars to the Milky Way's tidal field, its stream growing longer and denser as the dwarf itself shrinks and eventually dissolves. After the first close passage, the two merging galaxies do not immediately coalesce into one. The orbital energy has been reduced but not eliminated. The galaxies separate again, moving apart on their now decayed orbit, and then fall back together for a second passage, and perhaps a third and a fourth, each passage more destructive than the last, each one dissipating more orbital energy through dynamical friction and tidal interactions, until finally the orbital energy is insufficient to separate them and they merge permanently into a single system. This sequence of multiple passages and final coalescence, played out over hundreds of millions to a billion years, is vividly illustrated by computer simulations of galaxy mergers that have become one of the most powerful tools of theoretical astrophysics. Beginning in the 1970s with the pioneering work of Aller and Yuri Tomer, who showed that the disturbed morphologies of many observed interacting galaxy pairs could be reproduced by simple gravitational simulations of colliding point mass systems. Galaxy merger simulations have grown steadily in sophistication and realism. Modern merger simulations include not just the gravitational dynamics of stars and dark matter but also the hydrodynamics of the gas, the physics of star formation and stellar feedback, the effects of supermassive black holes and their feedback, and the detailed microphysics of the interstellar medium. They can reproduce the observed properties of merging galaxy pairs with remarkable fidelity, from the shapes of the tidal tails to the spatial distribution of star-forming regions to the kinematics of the stars and gas in the merger remnant. What these simulations show, and what the observations of merging galaxies at different stages confirm, is that the final coalescence of two comparably massive spiral galaxies produces a remnant that looks nothing like either of the original galaxies. The thin, cold, rotationally supported disks of the two spirals are heated and thickened by the violent gravitational perturbations of the merger. The stars, which were following orderly circular orbits in the disk, are scattered into a broad distribution of tilted, precessing, elliptical orbits that collectively form a smooth, roughly spheroidal or ellipsoidal distribution. The gas, driven inward by gravitational torques during the merger, is consumed in the central starburst or expelled by the AGN activity triggered by the inflow. The result, after the violence subsides and gravity draws the scattered stars into a new equilibrium over a few 100 million years, is an elliptical galaxy. Smooth, featureless, composed entirely of old stars, with no disk and no spiral arms and little or no ongoing star formation. The merger has transformed two living, active, star-forming spiral galaxies into a single, quiescent, red and dead elliptical. This transformation, spiral plus spiral equals elliptical, is one of the most fundamental pathways in galaxy evolution. It is the origin of the most massive galaxies in the universe. Every giant elliptical galaxy in every galaxy cluster is the product of this process, repeated many times over billions of years, each merger adding mass and complexity to the growing elliptical remnant. Among the many consequences of galaxy mergers, few are as dramatic or as cosmologically important as the starburst. When two gas-rich galaxies collide and merge, the gravitational torques of the interaction drive large quantities of gas toward the central regions of the merging system, compressing it, shocking it, and rapidly cooling it to the temperatures and densities required for star formation. The result is a starburst, an episode of star formation that can exceed the normal star formation rates of either progenitor galaxy by factors of 10 to 100 or more. Starburst galaxies are among the most luminous objects in the universe at infrared wavelengths. The intense ultraviolet radiation produced by the massive young stars born in the starburst is absorbed by the abundant dust in the gas-rich merging system and re-radiated as thermal infrared emission. A major merger starburst can produce infrared luminosities comparable to those of quasars, outshining at infrared wavelengths the combined light of hundreds of billions of ordinary stars. The most luminous of these objects, called ultraluminous infrared galaxies, or ULIRGs, are the most luminous galaxies in the local universe and are almost invariably found in systems showing clear morphological signs of recent or ongoing major mergers. The starburst is brief but intense. The gas driving the starburst is consumed rapidly at the elevated star formation rates, and the feedback from the massive stars being formed, the supernovae and radiation-driven winds, heats and disperses the remaining gas. A major merger starburst may last only a few tens of millions of years before the gas supply is exhausted, a short interval on galactic timescales but one during which an enormous amount of stellar mass is assembled. Some of the most massive and densely packed stellar systems known, including certain ultra-compact dwarf galaxies and the extremely dense, massive elliptical galaxies found in some clusters, may be the remnants of the central star-forming regions of merger-driven starbursts, the stellar nurseries of ancient collisions compressed and preserved over billions of years. The Milky Way itself has experienced starburst episodes in its past, triggered by the merger events that built up its structure. The thick disk of the Milky Way, the older, kinematically hotter stellar component above and below the thin disk, may include a significant contribution from a starburst triggered by the Gaia-Enceladus merger that occurred 8 to 10 billion years ago. The central molecular zone, the dense concentration of molecular gas within a few hundred light-years of the galactic center, shows evidence of episodic bursts of star formation that may have been triggered by past tidal interactions with satellite galaxies or by periodic inflows of gas driven by the galactic bar. Not all galaxy mergers are between comparable mass systems. In fact, the most common type of merger in the universe is the minor merger, the accretion of a small satellite galaxy by a much larger host. For every major merger between two galaxies of similar mass, a large galaxy like the Milky Way has experienced dozens or hundreds of minor mergers, absorbing dwarf galaxies and globular clusters and protogalactic fragments over its lifetime. Minor mergers are less dramatically transformative than major mergers, but they are not without consequences. A satellite galaxy falling into a larger host is tidally disrupted as it approaches, its outer stars stripped away by the host's tidal field and scattered into the host's halo as stellar streams. The stripped stars gradually mix into the host's stellar halo over billions of years, contributing to the diffuse stellar background that surrounds every large galaxy. The more compact central region of the satellite, denser and therefore more resistant to tidal disruption, may survive longer, eventually sinking to the center of the host galaxy through dynamical friction and depositing its stars in the host's central bulge or even near the central black hole. The globular clusters that orbit the Milky Way and its halo, ancient, dense stellar systems each containing hundreds of thousands to millions of stars, are themselves largely the nuclei of dwarf galaxies accreted in past minor mergers. The stripped outer envelopes of those dwarf galaxies have long since mixed into the Milky Way's halo, but the dense central nuclei, bound tightly enough to resist tidal disruption, survived and are now recognizable as the globular clusters we observe today. The Milky Way's approximately 150 known globular clusters are, in a very real sense, the collected trophies of a billion years of minor mergers. Minor mergers also contribute to the growth of galactic disks and halos in subtler ways. Gas brought in by accreting satellites, if they are gas-rich dwarf irregulars rather than gas-poor dwarf spheroidals, can fuel star formation in the host galaxy. The gravitational perturbations of orbiting satellites can thicken the host's disk, heat its stellar population, and excite spiral structure and other non-axisymmetric features. And the dark matter of accreted satellites is deposited into the host's dark matter halo, gradually increasing its mass and altering its density profile. The Milky Way's current satellite system, the population of dwarf galaxies and dwarf spheroidals that orbit in the Milky Way's halo, represents the galaxies that have not yet been fully accreted. The Large and Small Magellanic Clouds, the two most massive and most easily visible Milky Way satellites, are currently in their first or second close approach to the Milky Way and will eventually be tidally disrupted and absorbed over the next few billion years. The Sagittarius dwarf, as we noted earlier, is already in the process of being disrupted. The dozens of fainter dwarf galaxies in the outer halo are, on the cosmic timescale, temporary residents, passing through the Milky Way's sphere of influence on orbits that will eventually bring them close enough to be tidally torn apart and absorbed. Every large galaxy is constantly consuming its smaller neighbors. Slowly. Patiently. One dwarf galaxy at a time. The evidence of this consumption is written in the stellar streams and substructures of galactic halos, in the chemical compositions of halo stars, in the kinematics of the globular cluster system. The galaxy is an ongoing construction project, assembling itself through the accumulated accretion of everything that falls within its gravitational reach. Galaxy mergers were more frequent in the early universe than they are today, for the simple reason that the universe was smaller and denser then, and galaxies were closer together. The rate at which galaxy pairs merge, called the galaxy merger rate, has declined over cosmic time as the universe has expanded and the density of galaxies in any given volume of space has decreased. Observations of the merger fraction, the fraction of galaxies at any given epoch that show morphological signs of an ongoing or recent merger, confirm this theoretical expectation. At high redshifts, in the universe as it was 2 to 4 billion years after the Big Bang, the merger fraction is substantially higher than it is today. Irregular, disturbed, asymmetric galaxy morphologies are more common in the distant universe. the violence of major mergers is more evident. The universe at cosmic noon was not only forming stars more vigorously than today, it was also merging galaxies more frequently, and the two phenomena are connected, because mergers drive starbursts that contribute to the elevated star formation rates of the early universe. In the present-day universe, major mergers between comparable mass galaxies are relatively rare events. The Milky Way's impending collision with Andromeda is unusual in the local universe, a major merger event in a region that is otherwise dominated by the more gentle processes of minor mergers and gas accretion. Most of the galaxy evolution occurring in today's universe is happening at a quieter, slower pace than the turbulent early universe, a reflection of the declining merger rate and the declining availability of cold gas. But the mergers have not stopped. They are ongoing. Every galaxy cluster contains ongoing merger activity, smaller galaxies falling into larger ones, groups of galaxies falling into the cluster potential, the intracluster light growing as tidal stripping scatters stars into the space between galaxies. And even in the lower density environments of galaxy groups in the field, minor mergers and flyby interactions continue to shape the structural and star formation properties of individual galaxies on timescales of billions of years. The universe is still building, still assembling, still rearranging its matter into new configurations through the slow, patient, occasionally violent process of gravitational interaction. The galaxies we see today are not finished products. They are works in progress, shaped by their past mergers and still being shaped by their current and future interactions. The islands are still colliding. Slowly, grandly, in the dark. A galaxy can die. Not in the way a star dies, not in any explosive or dramatic sense, not in a collapse or an eruption or a sudden darkness. A galaxy dies quietly, slowly, over hundreds of millions of years. It simply stops making new stars. The young blue stars that gave it its brilliant color burn through their fuel and expire, not replaced by new ones. The galaxy fades from the vivid blue-white of active star formation to the warmer gold and red of an aging stellar population, growing dimmer and more quiescent decade by decade, billion year by billion year, until its remaining stars are all old, all cool, all slowly cooling toward the long darkness of the stellar graveyard. Astronomers call this process quenching, the extinguishing of a galaxy's star formation. The transition from the blue, actively star-forming galaxies of the young universe to the red, passively evolving galaxies that dominate the present-day population of massive galaxies. And it is one of the most important and most actively studied processes in all of galaxy evolution, because it determines the ultimate fate of individual galaxies and because understanding it is essential to understanding why the present-day universe looks the way it does. Look at the galaxy population today and you see a striking bimodality. Galaxies are not uniformly distributed in a continuous range of colors and star formation rates. They cluster into two distinct groups: blue, star-forming galaxies with ongoing star formation, young stellar populations, and abundant cold gas, and red, quiescent galaxies with no significant star formation, old stellar populations, and little cold gas. There is a relatively underpopulated region between these two groups, sometimes called the Green Valley, through which galaxies must pass as they transition from star-forming to quiescent. What drives a galaxy across the Green Valley? What quenches it? What takes a brilliant, star-forming spiral and turns it into a red, dead elliptical? These are the questions this chapter explores. The color magnitude diagram, a plot of galaxy color versus galaxy luminosity, is one of the most revealing tools in observational galaxy evolution. When thousands of galaxies are plotted in this diagram, a clear bimodal distribution emerges. The blue cloud, a broad sequence of actively star-forming galaxies at the blue end of the color axis, stretching from faint dwarf irregulars to moderately luminous spirals. The red sequence, a tight, narrow locus of quiescent, red galaxies at the red end of the color axis, populated predominantly by elliptical and lenticular galaxies. Tight because the stellar populations of quiescent galaxies are well characterized and their colors predictable from their ages and metallicities. And between them, the Green Valley, a region of intermediate color and intermediate star formation rate, sparsely populated compared to either the blue cloud or the red sequence, through which galaxies must transit as they make the transition from star forming to quiescent. The sparseness of the Green Valley tells us something important. The transition is relatively fast. If galaxies lingered in the Green Valley for billions of years, the valley would be as populated as the surrounding regions. Its relative emptiness implies that the quenching process, once initiated, operates on timescales shorter than the age of the universe, perhaps a few 100 million to a billion years for the most rapid quenching mechanisms. Understanding the Green Valley means understanding what triggers the transition and what physical processes drive it. Multiple mechanisms have been identified, operating at different mass scales and in different environments, and the quenching of any individual galaxy likely involves a combination of them rather than a single dominant process. Among the candidate quenching mechanisms, AGN feedback, the energetic output of the central supermassive black hole, holds a particularly prominent place in theoretical models of galaxy evolution. We discussed AGN feedback in the previous chapter in the context of the M-sigma relation and the regulation of black hole growth. Here we consider its role specifically in quenching star formation. The basic idea is straightforward. A galaxy undergoing a major merger, or accumulating gas rapidly through cold accretion from the cosmic web, drives large quantities of gas into its central regions. This gas feeds both a starburst and the central black hole. The black hole, accreting at a high rate, enters its quasar phase, pouring out radiation and driving powerful winds. These winds interact with the galaxy's interstellar medium, heating it, expelling it, and preventing it from cooling back to the temperatures and densities required for star formation. The starburst consumes or disperses the remaining cold gas. And when the process is complete, the galaxy is left without the cold gas fuel it needs to continue forming stars. It is quenched. This quasar mode feedback quenching is thought to be most effective for massive galaxies undergoing major mergers, because major mergers are the most efficient mechanism for driving large quantities of gas to the galactic center and triggering both intense star formation and vigorous black hole accretion simultaneously. The characteristic observational signature of this process is a powerful AGN-driven outflow co-spatial with a starburst, and such systems are indeed observed in the local universe and at high redshifts, precisely in the type of gas-rich major mergers where the theory predicts they should occur. After the quasar phase fades and the gas is depleted, the black hole enters the radio mode, its lower luminosity but mechanically powerful jet-driven phase. In this mode, The black hole continues to heat the surrounding gas through jet-inflated bubbles and sound waves propagating through the hot halo gas, preventing the hot gas from cooling and reforming the cold gas reservoir that could reignite star formation. Radio mode feedback acts as a maintenance mechanism, keeping already quenched galaxies quenched by offsetting the cooling of their hot gaseous halos over long timescales. This two-stage picture, quasar mode for initial quenching and radio mode for maintenance, is attractive and broadly consistent with observations. But it is not the whole story. Many massive quiescent galaxies show no signs of current or recent AGN activity, yet remain quenched. Many lower mass quiescent galaxies appear to have been quenched by environmental processes rather than by their own black holes. And the detailed physics of how AGN feedback energy couples to the galaxy's gas on galactic scales, bypassing the enormous range in physical scales between the black hole's immediate environment and the galaxy as a whole, remains incompletely understood. Not all quenching is driven by internal processes. For galaxies that live in rich galaxy clusters, the environment itself can be a powerful quenching agent, removing the gas supply and shutting down star formation through several distinct physical mechanisms. The most dramatic of these is ram pressure stripping. As a galaxy moves through the hot, dense intracluster medium, the intergalactic plasma that fills the space between galaxies in a cluster, it experiences a pressure from the gas rushing past it, just as a cyclist moving through air experiences a headwind. If this ram pressure is strong enough, it can exceed the gravitational restoring force that holds the galaxy's own gas in its disk, stripping the cold interstellar gas out of the galaxy and leaving it behind in a trail as the galaxy moves through the cluster. The stripped gas is heated by the hot intracluster medium and dispersed into the cluster environment, no longer available for star formation in the galaxy. The galaxy, deprived of its cold gas supply, begins to quench. Its existing stellar population continues to evolve passively, with the youngest and most massive stars dying first and the stellar light gradually reddening as the young blue stars disappear and the older red stars dominate. Over a few billion years, the galaxy transitions from the blue cloud to the red sequence, driven not by any internal process but simply by the environmental removal of its fuel. Ram pressure stripping is now directly observable in nearby galaxy clusters. Deep images and radio observations have revealed spectacular examples of galaxies being stripped of their gas as they fall into clusters, their cold gas drawn out into long tails extending behind them like the vapor trails of aircraft, sometimes stretching for hundreds of thousands of light years. The gas in these tails can itself form new stars, producing a phenomenon called jellyfish galaxies because of their visual resemblance to the marine animal, with the galaxy body intact and the gas tail extending behind it, star-forming regions glowing along the length of the tail like luminescent tentacles. A second environmental process is strangulation or starvation, a gentler but equally effective mechanism. As a galaxy falls into a cluster, the cluster's gravity strips away the galaxy's hot gaseous halo, the reservoir of warm gas in the galaxy's outer regions that would otherwise gradually cool and rain down onto the disk to replenish the cold gas supply for star formation. Without this hot halo replenishment, the galaxy can continue to form stars from its existing cold gas supply for some time, perhaps a few billion years, before the cold gas is exhausted and star formation ceases. The galaxy is not stripped of its existing gas but is cut off from the resupply that would allow it to continue forming stars indefinitely. Strangulation produces a slower quenching than ram pressure stripping, consistent with the observation that many cluster galaxies show intermediate colors and reduced, but not zero, star formation rates, suggesting a gradual decline rather than a sudden cutoff. The timescale for strangulation to fully quench a galaxy is estimated at 1 to several billion years, longer than the few 100 million years of ram pressure stripping. A third environmental mechanism is galaxy harassment, the cumulative effect of multiple rapid gravitational encounters between a galaxy and other cluster members as it orbits through the dense cluster environment. Each encounter perturbs the galaxy's stellar and gaseous structure, heating the disk, driving gas toward the center or out of the galaxy entirely, and gradually transforming the galaxy's morphology from a disk-dominated spiral to a more diffuse, less organized system. Harassment is most effective for lower-mass galaxies with shallower potential wells that are more easily disrupted by gravitational perturbations. Once a galaxy is quenched, what happens to it? It does not simply stop and freeze at the moment of quenching. It continues to evolve, passively, driven not by ongoing star formation but by the slow aging of its existing stellar population. The most massive stars in a quenched galaxy die first. Stars above roughly 8 solar masses live only millions of years and have already died long before the galaxy is quenched. Stars like the Sun live 10 billion years. The slightly less massive stars that remain in a quenched galaxy will live billions of years longer before they too exhaust their hydrogen and evolve off the main sequence. As these stars evolve, they pass through the red giant and asymptotic giant branch phases, becoming bright and red before shedding their outer envelopes and leaving white dwarf remnants. The color of a quenched galaxy evolves slowly but systematically over cosmic time. Immediately after quenching, the stellar population still contains relatively young, moderately massive stars that give the galaxy a somewhat bluer color than a truly ancient population. As these stars age and die, the galaxy's color reddens progressively, moving along the red sequence toward the colors characteristic of the oldest, most metal-rich stellar populations. This passive reddening is slow, taking billions of years to be noticeable, but it means that the red sequence galaxies we observe today at different redshifts have systematically different stellar population ages. The red sequence galaxies at high redshift, seen as they were several billion years ago, are bluer than the red sequence galaxies we see nearby, because their stellar populations were younger at the time we observed them. The size of quenched galaxies also evolves over cosmic time, but in a surprising direction. The most massive quiescent galaxies observed at high redshifts are significantly smaller than equally massive quiescent galaxies in the nearby universe, by factors of 3 to 5 in effective radius. A massive elliptical galaxy in the early universe, quenched when the universe was a few billion years old, appears to be compact, perhaps only a kiloparsec or so in half-light radius, while its present-day counterpart of the same mass is much more extended, with a half-light radius of 10 kiloparsecs or more. This size evolution of quiescent galaxies is one of the most striking observational facts of galaxy evolution and one of the most actively debated. How does a galaxy that has stopped forming stars grow in size by a factor of several over the subsequent billions of years? The most widely accepted answer is through minor mergers. Even after a massive galaxy has quenched its star formation, it continues to accrete small satellite galaxies through minor mergers. These minor mergers add stars to the outer regions of the galaxy, puffing it up and extending its effective radius without significantly increasing its mass, because the satellites are much less massive than the host. The galaxy grows from the outside in, gradually accumulating an extended stellar envelope of accreted stars while its core remains relatively compact and unchanged. This picture is consistent with the observation that the cores of massive present-day ellipticals, their central regions at densities comparable to the compact high-redshift ellipticals, appear similar to the high-redshift galaxies in their stellar population properties. The growth has occurred in the outskirts, not in the center. The galaxy has been wrapped in a growing cocoon of accreted stars while its original compact core sits essentially undisturbed inside. The process of quenching, operating across the galaxy population over billions of years, has changed the overall color of the universe. This is not a metaphor. The integrated light of all the galaxies in the universe, combined into a single spectrum, has a measurable color that reflects the mix of stellar populations currently forming stars and those that have been quenched and are aging passively. And that color has changed over cosmic time. In the early universe, when star formation rates were high and the galaxy population was dominated by young, actively star-forming systems, the universe was blue. Brilliant, intense, blue-white, blazing with the ultraviolet and blue light of massive young stars being born at cosmic noon. The integrated light of the cosmos was dominated by the output of these vigorous, gas-rich, star-forming systems. In the present-day universe, the situation is different. A substantial fraction of the stellar mass in the universe, concentrated in the most massive galaxies, is locked up in quiescent, red sequence galaxies that are no longer forming stars. The blue cloud is still present, still populated by star-forming spirals and irregulars, still producing new stars. But the massive quiescent galaxies, with their old red stellar populations, contribute a large fraction of the total optical light of the universe, tipping the integrated color toward the red. The present-day color of the universe, the average color of all the light emitted by all the galaxies, has been calculated from survey data and found to be a light beige, a pale cosmic latte as some astronomers have described it. Not the brilliant blue of the early universe, not the deep red of a fully quenched future, but a warm intermediate tone reflecting the mixture of young and old, active and quiescent, blue cloud and red sequence that characterizes the present epoch of cosmic history. The universe is aging. Its overall color is shifting slowly, inexorably, from blue toward red, as galaxy after galaxy is quenched and its stellar population ages. The rate of star formation in the universe is declining, as we discussed earlier. The blue cloud is losing members to the red sequence at a rate that exceeds the rate at which new star-forming galaxies are being created. The cosmos is transitioning, slowly, from its brilliant youth to a quieter, redder middle age. We are living in that transition. The universe around us is neither at its most brilliant nor at its most quiescent. It is in the long, slow shift between the two, a cosmic afternoon in which many of the most active processes of galactic youth are fading, but the darkness of the fully quenched future is still billions of years away. Every galaxy has a biography. A particular sequence of events, accidents, collisions, accretions, and quiescences that make its history unique among the 2 trillion other histories being written simultaneously across the observable universe. No 2 galaxies have the same history. No 2 galaxies arrived at their present state by the same path. The processes are universal. The outcomes are individual. The Milky Way's biography is the one we know best. Not because it is the most dramatic, or the most massive, or the most unusual, but because we are inside it. Because the evidence of its history is all around us, written in the motions of the stars overhead and the chemical compositions of ancient stellar populations and the streams of tidal debris arcing across the sky and the massive remnant of a past merger event sitting invisible in the infrared light of the galactic halo. We live inside a historical document, and we are only now, with the tools of modern astronomy, learning to read it. The Milky Way's story spans 13 billion years. It begins in the dark, in the chaos of the early universe, with the first tiny proto-galactic fragments assembling in the dark matter halos of a cosmos not yet 2 billion years old. It passes through a violent youth of mergers and starbursts and the blazing of a young active nucleus. It settles into a long middle age of steady star formation and gentle satellite accretion and the slow, patient building of a disk. And it approaches, now, the beginning of a new chapter, a great collision with its nearest large neighbor that will transform it, over the next several billion years, into something it has never been before. This is the story of our home. The Milky Way's history begins approximately 13 to 13.5 billion years ago, within the first billion years after the Big Bang. The evidence for this ancient beginning is found in the oldest stars in the galaxy, the extremely metal-poor stars of the inner halo and the ancient globular clusters, whose chemical compositions and age estimates place them in the first few 100 million to first billion years of the universe's history. The most metal-poor stars in the Milky Way, those with iron abundances less than 1/10,000th of the Sun's, are the chemical fossils of the earliest stellar generations. They formed from gas that had been only lightly enriched by the first population 3 stars, the massive, metal-free stars that formed in the very first dark matter halos and that died in the prodigious supernovae that scattered the first heavy elements into the primordial gas. These ancient, metal-poor stars carry in their chemical compositions the imprint of those first stellar deaths, the specific nucleosynthetic yields of the first supernovae preserved in their atmospheres for billions of years, readable today by high-resolution spectroscopy. The spatial distribution of these ancient stars tells us something about how the Milky Way assembled. They are found predominantly in the inner halo and bulge, the oldest structural components of the galaxy, concentrated near the center where the density was highest and where star formation began earliest. The proto-Milky Way in its first billion years was not the grand spiral we inhabit today. It was a chaotic, irregular assemblage of several proto-galactic fragments, merging and colliding and building up the first concentrations of stars in the inner galaxy. The globular clusters of the Milky Way, those ancient, dense stellar systems we discussed in the context of minor mergers, record the history of this early assembly. The oldest globular clusters, with ages of 13 to 13.5 billion years, are among the oldest objects in the universe whose ages can be reliably measured. They formed in the first proto-galactic fragments that would eventually become the Milky Way, before the disk existed, before the spiral arms, before the bar. They are the oldest surviving structures in our galaxy, relics of the primordial assembly that predate almost everything else we see around us. Between approximately 8 and 10 billion years ago, when the Milky Way was between 3 and 5 billion years old, something dramatic happened. A galaxy of roughly a quarter of the Milky Way's current stellar mass, a substantial system by any measure, fell into the young Milky Way and merged with it in a major merger event that left profound and lasting marks on the galaxy's structure. This ancient merger was discovered not through direct observation of the event, which occurred billions of years before any telescope existed, but through the pattern it left in the kinematics and chemical compositions of the Milky Way's halo stars, revealed by the extraordinary precision of the Gaia satellite's astrometric measurements. The accreted galaxy, now called Gaia Enceladus or the Gaia Sausage, deposited its stars into the inner halo of the Milky Way on highly radial orbits that take the stars far out into the halo and then back deep into the inner galaxy, their elongated paths leaving a characteristic signature in the distribution of stellar velocities that Gaia's measurements made it possible to identify. The Gaia-Enceladus merger was not a gentle event. It was a major merger, involving two comparably massive systems colliding and coalescing over hundreds of millions of years. The merger would have disturbed the young Milky Way's disk profoundly, heating it, thickening it, and perhaps triggering a significant burst of star formation as the gas of both galaxies was compressed and driven toward the centers of the merging systems. The thick disk of the Milky Way, the older, kinematically hotter stellar component that sits above and below the thin disk of younger stars, is now thought to have formed primarily during or shortly after the Gaia-Enceladus merger, its stars born in the starburst triggered by the collision. The metal-poor stars of the inner halo, long thought to be among the oldest and most ancient members of the galaxy, are now understood to include a large contribution from the accreted Gaia-Enceladus stars. The inner halo is not purely a primordial structure. It is a palimpsest, a document written over, with the original text of the Milky Way's own earliest stars overlaid by the contributions of the major merger. Distinguishing the two populations requires careful analysis of the star's orbits, chemical compositions, and ages, a task that Gaia and follow-up spectroscopic surveys are making increasingly possible. The Gaia-Enceladus merger also left a legacy in the Milky Way's globular cluster system. Many of the globular clusters currently orbiting in the Milky Way's halo were not born in the Milky Way itself. They were born in the Gaia-Enceladus galaxy and were accreted along with their host galaxy when it merged. Identifying which globular clusters are native Milky Way clusters and which are former Gaia-Enceladus clusters, based on their orbital properties and chemical compositions, is one of the active research areas in Milky Way archaeology. After the upheaval of the Gaia-Enceladus merger, the Milky Way entered a long period of relative stability and steady evolution that produced its most familiar structure, the thin disk. The thin disk is the flat, rotating component of the galaxy in which most of the ongoing star formation occurs, in which the spiral arms are found, in which the Sun resides, and in which the majority of the galaxy's young stars live. It is, in a very direct sense, the Milky Way as most people imagine it. The thin disk began to form approximately 8 to 9 billion years ago, in the aftermath of the Gaia-Enceladus merger, as the disturbed gas of the young Milky Way settled back into a rotating disk configuration. The earliest thin disk stars, now identifiable as the old, slightly metal-poor population of the inner thin disk, formed during this settling phase, before the disk had acquired the chemical enrichment that characterizes its younger stellar populations. Over the subsequent 8 to 9 billion years, The thin disk grew steadily through a combination of continued star formation from the existing gas reservoir and the accretion of new gas from the intergalactic medium and from the tidal disruption of infalling satellite galaxies. Stars formed, lived, died, and enriched the gas with heavy elements that were incorporated into the next generation of stars. The chemical enrichment history of the thin disk is recorded in the compositions of its stars. Older stars, formed earlier when the disk was less enriched, have lower abundances of iron and other heavy elements, while younger stars, formed from more processed gas, are more metal-rich. The Sun is a product of this long, steady thin disk evolution. Formed approximately 4.5 billion years ago from a cloud of gas in one of the Milky Way's spiral arms, the Sun inherited the chemical enrichment of roughly 9 billion years of prior stellar evolution in the galaxy. Its composition, with an iron abundance close to the average for stars of its age in the disk, reflects the typical enrichment level reached by the disk gas by the time of its formation. The Sun is neither unusually metal-rich nor unusually metal-poor for its age and location. It is, in chemical terms, a thoroughly typical thin disk star. And everything that makes life on Earth possible, every atom of carbon and oxygen and nitrogen and phosphorus and iron and calcium and the dozens of other elements essential to biochemistry, was forged in stars that lived and died in the thin disk before the Sun was born, returned to the interstellar medium by stellar winds and supernovae, mixed into the gas cloud that became the solar nebula, and ultimately incorporated into the Earth and into the bodies of every living thing that has ever existed on its surface. You are a product of the thin disk's 9 billion year chemical evolution. The Milky Way made you, atom by atom, over a span of time longer than the current age of the solar system. The Milky Way does not travel alone. It is accompanied by a retinue of smaller galaxies, the satellite galaxies, that orbit within its dark matter halo and that represent the smaller end of the hierarchical assembly process that built the galaxy over billions of years. Understanding the satellite system of the Milky Way is both intrinsically interesting as a study of the smallest galaxies and cosmologically important as a test of the standard model of galaxy formation. The most prominent and most massive satellites are the Large and Small Magellanic Clouds, visible from the southern hemisphere as two detached patches of the Milky Way's band. Irregular galaxies of considerable size containing respectively roughly 10 billion and 2 billion stars. The Large Magellanic Cloud is the fourth largest galaxy in the local group, after the Milky Way, Andromeda, and the Triangulum Galaxy. It is currently undergoing active star formation, its Tarantula Nebula one of the most prodigious star-forming regions in the local group, containing some of the most massive stars known. The Magellanic Clouds are currently making their first or perhaps second close approach to the Milky Way, having fallen in from the broader local group environment relatively recently in cosmic terms. Their interaction with the Milky Way is already leaving marks. The Magellanic Stream, a long arc of gas stretching almost halfway around the sky, is gas stripped from the Magellanic Clouds by tidal forces and ram pressure as they orbit through the Milky Way's halo. The stream contains enough gas to fuel a significant burst of star formation in the Milky Way if and when it falls into the galactic disk. Beyond the Magellanic Clouds, the Milky Way hosts a population of smaller dwarf spheroidal and ultra-faint dwarf galaxies scattered through its halo. These are the faintest, most dark matter-dominated galaxies known, some containing only a few hundred to a few thousand stars. their luminosity so low that they are challenging to detect even in the local universe. The ultra-faint dwarfs discovered by large sky surveys in the past 2 decades, many of them hiding in plain sight in survey data until sophisticated detection algorithms picked them out of the stellar background, have substantially increased the known satellite count and are providing important constraints on the nature of dark matter and the physics of galaxy formation at the smallest scales. The Milky Way's satellite system is also the stage for one of the longest-running puzzles in near-field cosmology, the missing satellites problem. Simulations of dark matter halo formation predict many more small dark matter subhalos within a galaxy-sized halo than the number of observed satellite galaxies. The discrepancy between predicted and observed satellite counts was once thought to be a fundamental problem for the standard cold dark matter model. It is now understood to be at least partially resolved by the physics of galaxy formation. Most of the predicted dark matter subhalos are too small or too dense to have retained enough gas to form stars, either because reionization photoevaporated their gas before it could cool and collapse, or because supernova feedback expelled it. The tiny ultra-faint dwarfs being discovered in ongoing surveys may be the tip of an iceberg of mostly dark, starless subhalos that fill the Milky Way's halo invisibly. The discipline of galactic archaeology, sometimes called near-field cosmology, is the science of reconstructing the formation and evolution history of the Milky Way from the detailed properties of its present-day stellar populations. It is based on the principle that stars are long-lived records of the conditions at their birth. A star's chemical composition is fixed at formation and changes only slowly thereafter, preserving the composition of the gas from which it formed. A star's age can be estimated from its luminosity and temperature for stars at certain evolutionary stages. And a star's orbital kinematics, its current position and velocity in the galaxy, carry memory of how it was born and how it has been perturbed since. By measuring the chemical compositions, ages, and kinematics of large samples of stars across the Milky Way, galactic archaeologists piece together the fossil record of the galaxy's history, identifying distinct stellar populations associated with different formation events, tracing the chemical enrichment history of the disk and halo, mapping the substructures left by ancient mergers, and reconstructing the assembly sequence that built the galaxy from its primordial protogalactic fragments to its current form. The Gaia satellite, with its billion-star astrometric catalog, has transformed this field. For the first time, we have full 6-dimensional phase space information, 3 spatial coordinates and 3 velocity components, for millions of stars throughout the inner galaxy in its halo, making it possible to identify kinematic substructures, stellar streams, and accreted populations that were previously invisible in the 2-dimensional sky projection. Combined with large spectroscopic surveys that measure chemical abundances for hundreds of thousands of stars, the Gaia data has produced what amounts to a detailed biography of the Milky Way, written in the motions and compositions of its stellar population. Among the most important findings of this galactic archaeological program are the identification of the Gaia-Enceladus merger and several other significant ancient accretion events, the discovery that the thick disk and thin disk have distinct chemical and kinematic properties consistent with distinct formation histories, the mapping of multiple stellar streams in the halo corresponding to the tidal debris of disrupted satellite galaxies, and the determination that the Milky Way assembled the majority of its stellar mass in the first few billion years and has been growing more slowly since. The Milky Way is an open book. Its history is written in its stars, in the specific compositions and motions of hundreds of billions of individual suns, each one a data point in the reconstruction of 13 billion years of galactic evolution. We are, at this moment in the history of astronomy, reading that book with increasing clarity and increasing depth, deciphering the record of events that no one was there to observe, events that occurred billions of years before the first eye opened on the first planet, events whose consequences are all around us in the night sky tonight. The stars above you are not just beautiful. They are witnesses. They remember everything. Step back far enough from any individual galaxy, far enough that the galaxy itself becomes a point of light too small to resolve, far enough that you can see not just the galaxy but its neighbors, and its neighbors' neighbors, and the entire distribution of galaxies across hundreds of millions of light years, and something extraordinary becomes visible. The galaxies are not scattered randomly through space. They are organized, arranged, concentrated into structures of astonishing scale and complexity, structures that dwarf even the largest individual galaxy the way a forest dwarfs a single tree. Long filaments of galaxies stretching for hundreds of millions of light years, thin as threads relative to their length, connecting massive concentrations of galaxies at their nodes. Flat sheets of galaxies, two-dimensional walls enclosing enormous empty regions. And the empty regions themselves, vast cosmic voids hundreds of millions of light years across, nearly devoid of galaxies, occupying most of the universe's volume while containing only a small fraction of its matter. This is the cosmic web, the large-scale structure of the universe, the architecture within which all galaxies are embedded, the framework that shapes their distribution across the cosmos, the scaffolding of dark matter and gas and gravity that connects the smallest protogalactic fragment to the largest supercluster and organizes the entire visible universe into a single, continuous, intricate network. Galaxies are not isolated islands. They are nodes in a web. And understanding what that web is, how it formed, and how it shapes the evolution of the galaxies within it is essential to understanding galaxies themselves. A galaxy cannot be fully understood in isolation. It must be understood in context, in relation to its position and history within the larger structure. The cosmic web is gravity's grandest creation. It emerged from the same process that created galaxies and galaxy clusters, the gravitational amplification of the tiny density fluctuations seeded by inflation in the primordial universe, but operating on larger scales and over longer timescales. In the early universe, the density fluctuations were present on all scales, from the tiny scales that would produce stars and galaxies to the large scales that would produce galaxy clusters and the cosmic web. The smaller scale fluctuations grew faster, because gravity operates more efficiently on denser, more compact structures, and collapsed into the first halos and galaxies while the larger scale fluctuations were still in their linear growth phase. But the large-scale fluctuations were always there, shaping the distribution of the forming galaxies and galaxy clusters even as they themselves remained uncollapsed. The cosmic web formed through a process called gravitational collapse along preferential axes. A region of space that is slightly overdense is not uniformly overdense in all directions. It has slightly different density gradients in different directions, meaning that gravity pulls matter toward it more strongly from some directions than others. The matter first collapses along the direction of steepest gradient, the shortest axis of the overdensity, forming a flat pancake or sheet. Then it collapses along the second axis, forming a filament. Finally, where filaments intersect, the material collapses along the third axis into the compact, roughly spherical concentrations that we call galaxy clusters. This sequence of collapse, from sheet to filament to node, naturally produces the web-like structure we observe. The sheets are the walls of the cosmic web, two-dimensional concentrations that enclose the voids. The filaments are the threads, the long, linear concentrations that connect the nodes and that carry the galaxies and gas flowing toward the cluster concentrations. And the nodes are the galaxy clusters, the densest, most massive concentrations of matter in the universe, sitting at the intersections of multiple filaments like knots in a net. The dark matter collapses into this web-like structure first. For the same reason it leads galaxy formation, it is not impeded by radiation pressure or gas dynamics. The ordinary matter follows, flowing along the dark matter filaments toward the dense nodes, feeding the galaxies that form within those nodes and along the filaments themselves. The cosmic web is primarily a dark matter structure, with the visible galaxies and gas tracing its skeleton like lights strung along an invisible framework. The filaments of the cosmic web are its most extensive structures, stretching for tens to hundreds of millions of light-years through space, connecting galaxy clusters across the cosmic landscape. They are not uniform tubes of matter. They are complex, multi-stranded structures, with inner cores of dark matter and hot gas and individual galaxy chains embedded within a broader, more diffuse envelope that tapers gradually to the surrounding voids. Galaxies and filaments are not randomly distributed along their length. They tend to concentrate near the densest parts of the filament, near its core, and to be more abundant at the ends of the filament where it connects to clusters. They tend to have properties intermediate between the isolated field galaxies in the voids and the cluster galaxies at the nodes, somewhat more likely to be in the process of quenching than field galaxies, somewhat more likely to have their gas supply depleted by the environment, but not as thoroughly quenched as the galaxies deep within clusters. The filaments also carry gas. Not the cold, dense gas of galactic disks, but a warm-hot intergalactic medium, gas at temperatures of 100,000 to 10 million degrees that fills the filaments and represents one of the largest reservoirs of baryonic matter in the universe. This warm-hot intergalactic medium, or WIM, is thought to contain a large fraction, perhaps 30 to 40%, of all the ordinary matter in the universe, distributed in the diffuse filamentary network rather than concentrated in galaxies or galaxy clusters. It is one of the most difficult components of the universe to observe directly, because its temperature and density put most of its emission in the extreme ultraviolet and soft X-ray bands where the observations are technically challenging, but it is gradually being mapped by sensitive X-ray and ultraviolet observatories. The filaments are not static. They carry flows of matter, streams of gas and dark matter moving along the filament axis toward the cluster nodes, feeding the growth of the clusters and the galaxies within them. These large-scale flows are driven by the gravitational attraction of the massive cluster concentrations at the filament ends, drawing matter from the surrounding regions in a slow, cosmic drainage. Galaxies in the filaments are not merely sitting still. They are being carried along the filament toward the cluster, their trajectories governed by the large-scale gravitational potential of the cosmic web, moving at hundreds of kilometers per second on journeys that take billions of years to complete. At the nodes of the cosmic web, where multiple filaments intersect and the dark matter concentration is greatest, the densest and most massive structures in the universe have assembled: galaxy clusters. These are gravitationally bound collections of hundreds to thousands of individual galaxies, embedded in an enormous dark matter halo and permeated by a hot, X-ray emitting intracluster medium, with total masses ranging from roughly 10 to the 14th to 10 to the 15th solar masses. The largest galaxy clusters are the most massive gravitationally bound objects in the universe. The Coma cluster, one of the nearby well-studied examples, contains over 1,000 cataloged galaxies and has a total mass of roughly 10 to the 15th solar masses, most of it in dark matter, with the hot intracluster medium contributing several times more mass than all the galaxies combined. The galaxies themselves, despite their enormous number and luminosity, are a minor constituent by mass of the cluster as a whole. Life in a galaxy cluster is harsh. The hot intracluster medium, at temperatures of tens of millions of degrees and detectable in X-ray images as a diffuse glow filling the cluster volume, strips cold gas from infalling galaxies through ram pressure. The high density of galaxies means frequent gravitational interactions and harassment that disturb galactic disks and drive morphological transformation. And the deep gravitational potential of the cluster accelerates galaxies to high velocities relative to each other, making mergers between cluster members rare and fast rather than slow and complete, a type of interaction called a flyby that can disturb galactic structure without producing full coalescence. As a result, galaxy clusters are dominated by early-type, quiescent galaxies. The classic morphology density relation, first clearly documented by Alan Dressler in 1980, shows that the fraction of elliptical and lenticular galaxies increases strongly with local galaxy density, from roughly 10 to 20% in the low-density field to over 70% in the cores of rich clusters. The cluster environment is a galaxy transformation machine, converting infalling spirals into quiescent lenticulars and ellipticals through the combined action of ram pressure stripping, harassment, and the aging of stellar populations cut off from their gas supply. At the very center of the richest clusters sits the brightest cluster galaxy, the most massive and most luminous galaxy in the universe, often a giant elliptical of extraordinary size with a stellar mass of several trillion solar masses, an extended diffuse stellar halo blending smoothly into the intracluster light, and an enormously massive central black hole. These central giants have grown to their spectacular sizes through the accumulated mergers of billions of years of cluster assembly, absorbing galaxy after galaxy as each fell to the cluster center through dynamical friction. They are the ultimate products of hierarchical assembly, the largest objects that gravity has managed to organize in the age of the universe. Between the filaments and sheets and clusters, occupying the vast majority of the universe's volume, are the voids. Regions of space hundreds of millions of light-years across in which the density of galaxies is far below the cosmic mean, where individual galaxies are rare and widely spaced, where the dark matter is diffuse and the gas is even more diffuse, where the cosmic web is absent and the universe is as close to empty as it ever gets on large scales. Voids are not truly empty. They contain galaxies, just far fewer than the average. A void galaxy is a galaxy living in one of the loneliest environments in the universe, far from any neighbor, insulated from the environmental processes that transform galaxies in denser environments, evolving primarily under the influence of its own internal processes rather than the external pressures of group or cluster membership. Void galaxies are, as a result, among the most pristine in the universe. They tend to be blue, actively star-forming, relatively gas-rich, and morphologically undisturbed, because they have not experienced the gas stripping, harassment, and tidal interactions that transform galaxies in denser environments. Studying void galaxies is a way of studying galaxy evolution in its simplest form, without the complicating effects of environment, providing a baseline against which the effects of environment in groups and clusters can be measured. The voids also expand. As the universe grows and the cosmic web continues to develop, the overdense regions of filaments and clusters continue to collapse and grow denser, while the underdense voids continue to expand and grow emptier. The voids are evacuating themselves, their matter draining away along the filaments toward the clusters, their size increasing over cosmic time as the structure of the web becomes more pronounced. The large voids of the present-day universe are larger and emptier than the voids of the early universe, the result of billions of years of continued structure formation deepening the contrast between the dense and empty regions. The Milky Way sits in a moderately underdense region of the universe, in the outskirts of the Virgo supercluster, which is itself one node of a much larger structure called the Laniakea supercluster. The local group, the cluster of galaxies containing the Milky Way and Andromeda, is a relatively modest structure in the cosmic web, not a rich cluster at a major filament node but a small group in a minor filament branch. We are, in the geography of the cosmic web, somewhat provincial. Not in a dense, active cluster but not in a void either. In a quiet suburban location, far from the most active and densely populated cosmic cities, in a neighborhood that has allowed the Milky Way to evolve relatively peacefully for most of its history. The cosmic web defines our address. The large-scale environment in which a galaxy lives shapes its evolution at every stage, from the gas supply available for star formation to the merger rate it experiences to the stripping processes it may undergo. The web is not merely a backdrop. It is a participant in the story of every galaxy it contains. And it is still forming. The cosmic web is not finished. It continues to develop, the density contrasts deepening, the clusters growing more massive, the voids growing emptier, the filaments carrying their patient flows of matter toward the nodes. The architecture of the universe is a work in progress, unfolding on timescales of billions of years, visible in its current state to every telescope that looks beyond our own galaxy into the larger structure of which we are so small a part. We live inside something enormous. Something still being built. Something whose full extent and full complexity we are only beginning to map and understand. The web holds us. It has always held us. And it always will. The light from distant galaxies takes time to reach us. The light from a galaxy 1 billion light-years away left that galaxy 1 billion years ago and has been traveling through the expanding universe ever since, its wavelength stretched by the expansion of space, before arriving at our telescopes and detectors tonight. We are not seeing that galaxy as it is now. We are seeing it as it was 1 billion years ago. This is not a limitation or a distortion of observation. It is a profound gift. It means that when we look at galaxies at different distances, we are not merely seeing galaxies in different locations. We are seeing galaxies at different times in the universe's history. The nearby galaxies show us the present. The moderately distant galaxies show us the universe as it was a few billion years ago. The most distant galaxies and the deepest images show us the universe as it was only a few 100 million years after the Big Bang, when the first galaxies were just assembling from their protogalactic fragments. A deep field image is therefore not merely a photograph of many galaxies at a single moment. It is a photograph of the universe's entire history, compressed along the depth axis, with nearby galaxies in the foreground representing the present and the faintest, most distant objects in the background representing the universe's infancy. Looking at a deep field image is looking simultaneously at the present and the past, at the mature, structured galaxies of today and the chaotic, irregular, intensely star-forming proto-galaxies of 10 to 13 billion years ago. And what the comparison reveals, the systematic differences between galaxies near and far, between the universe now and the universe then, is one of the most powerful direct demonstrations of galactic evolution ever obtained. The universe has changed. Galaxies have changed. The difference between the deep universe and the nearby universe is not merely one of distance. It is one of time, and therefore of development, of age, of the accumulated transformations that billions of years of evolution have produced. The original Hubble Deep Field of 1995, the 10-day exposure in Ursa Major, was followed by a second deep field in the southern sky in 1998, then the Hubble Deep Field South. Then, using the upgraded camera installed during the 1999 servicing mission, the Hubble Ultra Deep Field in 2004, a 23-day exposure in the constellation Fornax that reached galaxies even fainter and more distant than the original deep fields, revealing approximately 10,000 galaxies in a single image and extending the temporal reach of the survey to within approximately 400 million years of the Big Bang. In 2012, a portion of the ultra-deep field was reobserved with even longer exposures, producing the Hubble Extreme Deep Field, the deepest optical image of the universe ever obtained at the time, containing approximately 5,500 galaxies and reaching galaxies with redshifts greater than 8, corresponding to a time when the universe was less than 700 million years old. Each successive deep field pushed the frontier further, revealing fainter objects, higher redshift galaxies, earlier epochs in the universe's history. Each one showed the same systematic pattern. The most distant, earliest galaxies are different from the nearby, present-day ones. They are smaller, on average, more irregular in shape, more vigorously star-forming, their blue light dominated by the output of young, massive stars being born at extraordinary rates. More asymmetric, more disturbed, more actively merging. Less like the grand spirals and serene ellipticals of today and more like the raw, violent, creative chaos of a universe still figuring out what shape it wants to be. The transition between the early, irregular, vigorously star-forming universe and the more settled, more structured, more quiescent present-day universe is gradual but clear in the deep fields. At intermediate redshifts, at distances corresponding to look-back times of 5 to 8 billion years, the galaxy population is a mixture, some galaxies already recognizable as mature spirals or ellipticals, others still irregular and disturbed. The Milky Way at that epoch, if we could observe it from outside, would look different from the Milky Way today, its disk less settled, its star formation more vigorous, its spiral structure less organized and more chaotic. The Hubble Space Telescope's deep fields were limited by its primary mirror size and its sensitivity at visible and near-infrared wavelengths. The most distant galaxies, Those at the highest redshifts corresponding to the first few 100 million years after the Big Bang emit most of their light at ultraviolet wavelengths, but the expansion of the universe redshifts that light into the infrared by the time it reaches us. Hubble's sensitivity in the infrared was limited, and the most distant galaxies were at the very edge of what it could detect. The James Webb Space Telescope, with its 6.5-meter primary mirror and its detectors optimized for infrared wavelengths, was designed specifically to push the deep field frontier into the territory where the first galaxies formed. And since beginning science operations in mid-2022, it has done exactly that with a completeness and a clarity that has astonished even its designers. The first deep field image released from Webb in July 2022 showed galaxies at redshifts greater than 13, corresponding to a time less than 300 million years after the Big Bang, in extraordinary detail. Galaxies that had been barely detectable smudges in the deepest Hubble images were resolved by Webb into structured objects with identifiable morphological features, their colors and brightness distributions measurable with enough precision to constrain their stellar populations, star formation rates, and masses. What Webb found in the deep universe confirmed some theoretical expectations and challenged others. On the expected side, the high redshift galaxy population is indeed dominated by small, irregular, vigorously star-forming objects, consistent with the early stages of hierarchical assembly. On the surprising side, some of these very early galaxies are brighter, more massive, and more structured than the standard models predicted they should be. There are more massive, more luminous galaxies in the first billion years of cosmic history than the simulations suggested would exist. This excess of bright, massive early galaxies, sometimes described as the most serious challenge to the standard model of galaxy formation from current Webb observations, does not necessarily mean the standard model is wrong. It may indicate that star formation in the early universe was more efficient than assumed, converting gas to stars more completely and more rapidly. It may indicate that early galaxies were less dust-obscured than later ones, making them appear brighter for their stellar mass. It may indicate that the initial mass function of stars, the distribution of masses among newly formed stars, was different in the pristine gas of the early universe, producing more massive, brighter stars per unit mass of gas converted. Or it may indicate something more fundamental, some ingredient in the physics of early galaxy formation that the models are missing. The debate is active, the data are accumulating, and the answer, when it comes, will deepen our understanding of the first chapter of galactic history in ways that neither Hubble nor Webb has yet fully revealed. Deep field images reveal not just the evolution of typical galaxies but the extraordinary diversity of galactic forms at every epoch. Every deep field image is a zoo, a collection of shapes and sizes and colors and morphologies that no single descriptive vocabulary fully captures, that surprises the eye at every scale of examination, that rewards careful study with an endless stream of individual objects, each with its own story, its own history, its own particular path through cosmic time. This diversity prompted one of the most creative experiments in the history of scientific crowdsourcing. In 2007, a team of astronomers created a website called Galaxy Zoo, which presented ordinary members of the public with images of galaxies from the Sloan Digital Sky Survey and asked them to classify each one. Is it a spiral or an elliptical? If it is a spiral, which way does it wind? Is it disturbed or interacting? Does it have a bar? The response was extraordinary. Within 24 hours of the website's launch, volunteers were classifying galaxies at a rate of 70,000 per hour. Within the first year, more than 100,000 volunteers had collectively made tens of millions of galaxy classifications. The human brain's pattern recognition capabilities, applied at scale through citizen science, produced a morphological catalog of unprecedented size and quality, classified by human eyes rather than by automated algorithms that had struggled to match human performance on the subtleties of galaxy morphology. The Galaxy Zoo data revealed systematic patterns in galaxy morphology that had been difficult to study in smaller, manually classified samples. It confirmed and quantified the morphology-density relation, the tendency for elliptical and lenticular galaxies to be more common in denser environments. It revealed asymmetries in the chirality of spiral galaxies, the distribution of clockwise versus counterclockwise spirals, that provided constraints on the large-scale structure of the universe. And it produced a rich database of rare and unusual galaxy types, from ring galaxies formed in unusual head-on collisions to polar ring galaxies whose stellar rings orbit perpendicular to the main disk, each one a puzzle and a story. Galaxy Zoo has since expanded to deeper surveys and higher redshifts, and its volunteers are now classifying galaxies in the deep fields, providing morphological information on the early universe's galaxy population that complements the photometric and spectroscopic data from the great observatories. The human eye, even the untrained one, turns out to be an extraordinarily powerful tool for galaxy classification, sensitive to subtle structural features that automated algorithms consistently miss. The universe is more varied and more individually interesting than any model or simulation has fully captured. Every deep field image is a reminder of that variety, a reminder that the 2 trillion galaxies in the observable universe are not 2 trillion copies of the same object but 2 trillion individual histories, each one shaped by its particular sequence of mergers and accretions and quenchings and reactivations, each one a unique product of 13 billion years of cosmic creativity. No 2 galaxies are the same. No 2 histories are identical. The universe, for all its vast scale, is not monotonous. It is endlessly particular, endlessly surprising, endlessly itself. The Milky Way has existed for approximately 13 billion years. In that time it has assembled itself from protogalactic fragments, survived a major merger that built its inner halo and thick disk, formed hundreds of billions of stars across a thin rotating disk, built a bar that has been quietly driving gas inward for billions of years, and accreted dozens of satellite galaxies whose stellar debris still traces visible streams through its halo. It is, by any measure, a mature and richly structured galaxy, settled into the long Middle Age of steady, moderate star formation that will continue for billions of years to come. But the Milky Way story is far from over. The next several billion years will bring changes as dramatic as any in its past. A collision is coming. A collision that will not merely disturb the galaxy or strip some of its satellites, but will fundamentally transform it, merging it with its nearest large neighbor into something new and unprecedented in the local group. The collision with Andromeda. And beyond that collision, a future stretching billions of years further, in which the merged galaxy will evolve and fade and eventually, in the deepest future, go dark along with every other galaxy in the universe. Tonight we follow the Milky Way into that future. The Andromeda Galaxy, Messier 31, is the Milky Way's nearest large neighbor, a barred spiral galaxy slightly more massive than the Milky Way, containing perhaps 1 trillion stars to the Milky Way's 300 to 400 billion, located approximately 2.5 million light-years away in the constellation Andromeda. On a clear, dark night, far from city lights, Andromeda is the most distant object visible to the naked eye, a faint oval smudge just perceptible without optical aid, its light having traveled 2.5 million years to reach the retina. Andromeda is approaching. The Hubble Space Telescope's precise measurements of Andromeda's proper motion across the sky, combined with radial velocity measurements from spectroscopy, established in 2012 that Andromeda is on a nearly head-on collision course with the Milky Way, approaching at approximately 110 kilometers per second. The collision is not imminent on any human timescale, and the precise timing depends on the exact transverse velocity component, which is more difficult to measure. But the best current estimates place the first close approach approximately 4 billion years from now. 4 billion years. By the time of the collision, the Sun will be approaching the end of its main sequence life, swelling into a red giant, its luminosity increasing dramatically, its habitable zone migrating outward past the current orbits of Venus and Earth. Whether life on Earth, if it still exists in any form, will be present to experience the visual spectacle of the collision in the night sky is one of the most dramatic what-ifs in all of long-range speculative astronomy. During the collision, which will unfold over hundreds of millions of years in multiple passages before final coalescence, the night sky as seen from any surviving planet will be transformed. The familiar band of the Milky Way will be disturbed and distorted as the two galaxy disks interpenetrate. Andromeda, already visible as the faint Andromeda galaxy we see today, will grow larger and brighter in the sky as it approaches, eventually spanning a significant fraction of the entire sky. Tidal tails of stars will be drawn out from both galaxies, streaking across the sky in arcing paths visible to the naked eye. New stars will blaze into existence in the compressed gas of the merging disks, their blue-white light briefly illuminating the galactic turmoil. The Sun will almost certainly survive the collision. The probability of any individual star being struck by another star during the merger is negligible, because even in the densest regions of the merging galaxies the stars are separated by distances so large relative to their physical sizes that direct collisions are extraordinarily rare. But the Sun's orbit will be severely perturbed by the gravitational churning of the merger. It may be flung into a completely different part of the merged galaxy, perhaps into the outer halo, perhaps deep into the central regions, perhaps into a tidal tail that stretches far from the main body of the merger remnant. After the final coalescence, after the hundreds of millions of years of gravitational churning and tidal interaction and repeated passages have spent themselves and the combined system has settled into a new gravitational equilibrium, the result will be an elliptical galaxy. The two spirals, their disks destroyed by the violence of the merger, their stars scattered into chaotic orbits, will have merged into a single, smooth, featureless, slowly rotating elliptical. Astronomers have nicknamed this future galaxy Milkomeda or Milkdromeda, a portmanteau of its two progenitors. Milkomeda will be a red and dead elliptical. The merger will have triggered a final starburst that consumes much of the remaining cold gas, and the AGN activity awakened by the inflow of gas to the central black holes, which will themselves merge into a single more massive black hole, will heat and expel whatever gas the starburst does not consume. Without cold gas, without ongoing star formation, Without spiral arms or a bar or any of the structures that currently define the Milky Way's identity, Milkomeda will be something the Milky Way has never been: quiet, passive, red. The galaxy that contains the solar system, for a billion years from now, will look nothing like the galaxy we inhabit tonight. After the Andromeda merger, Milkomeda will continue to evolve passively over the billions of years that follow. Its stellar population will age, the hottest and brightest remaining stars gradually dying and leaving the cooler, more long-lived ones to dominate. The galaxy's color will redden further. Its luminosity will decline. The last star-forming regions, if any survive the merger, will eventually exhaust their gas and go dark. Minor mergers will continue. The smaller galaxies of the local group, the Triangulum Galaxy and the numerous dwarf galaxies orbiting both the Milky Way and Andromeda, will eventually fall into Milkomeda through the same dynamical friction that is bringing the Magellanic Clouds toward the Milky Way today. Each accretion will add a small contribution of stars and gas, the last stellar additions to a galaxy that is otherwise done building. The gas brought in by these final accretions may trigger brief, small episodes of star formation, modest flickers in the otherwise fading galaxy, before being consumed or expelled. In approximately 100 billion years, the last of the local group galaxies will have merged into the single remnant that Milkomeda has become by then. The local group will have collapsed into a single object, a massive elliptical galaxy floating alone in the void. All the other galaxy groups and clusters will be receding beyond the cosmic horizon, carried away by the accelerating expansion of the universe, no longer visible even in principle. The single merged local group galaxy, the last descendant of the Milky Way and Andromeda and all their companions, will be alone in an observable universe that contains only itself. And then the slow dying of its stars will begin in earnest. The sun-like stars will have already died billions of years earlier. The orange and yellow subgiant stars will follow. Eventually only the red dwarfs will remain, their dim crimson light the last illumination of a galaxy that once blazed with the combined light of trillions of stars. One by one, over trillions of years, the red dwarfs will exhaust their hydrogen and cool and fade to black dwarfs. The last star and the last descendant of the Milky Way will go out, somewhere between 10 and 100 trillion years from now, in darkness and silence. And the object that was once our galaxy, that once contained the sun and the earth and everything that has ever lived and thought and wondered on this world, will be a cold, dark, drifting collection of stellar remnants, orbiting each other in the profound silence of the far future universe. That is the fate of the Milky Way. The same fate awaits every galaxy. The same darkness, the same patience, the same long, slow cooling. But it is very far away. And tonight, the galaxy is alive. We have reached the end of our journey through the life of galaxies. 3 hours of slow, deep travel through 13 billion years of cosmic history, from the first proto-galactic fragments assembling in the dark matter web of the early universe to the distant future in which the Milky Way's last descendant will cool and fade to darkness. We have met spiral arms that are not structures but waves, and black holes that are not merely objects but regulatory mechanisms, and collisions that are not catastrophes but transformations, and the vast cosmic web within which every galaxy is embedded like a node in a net that spans the entire observable universe. I want to close not with a summary but with a feeling. A particular feeling that I think the material of this journey, properly absorbed, produces. A feeling that is difficult to name but that I suspect you may already be experiencing, if the journey has gone well and the hour is late and the room is quiet. It is the feeling of scale properly felt. Not merely known intellectually, in the way we know that the Milky Way is 100,000 light years across, but felt, in the particular way that only comes from spending a long time in the presence of something much larger than yourself. The feeling of being correctly sized. Of having your ordinary sense of scale and importance gently, permanently adjusted by an encounter with the truly immense. You live inside a galaxy. Not near one. Not in the vicinity of one. Inside one. The Milky Way is not something you observe from outside. It is the structure that contains you, that has contained you since before you were born, that contained every human being who ever lived and every organism that has evolved on this planet and every rock and ocean and atmosphere that this world has ever had. You have spent your entire existence inside a galaxy without ever being able to step outside it and see it whole. The band of light you see on a clear night, that soft, luminous arc stretching from horizon to horizon, is the inside view. The view from within. The perspective that no external observer can have. You are seeing your home from the inside. The way a fish sees the ocean not as the blue expanse visible from a cliff but as the medium it swims in every direction, always. And the galaxy itself, the structure within which your entire life has unfolded, is itself inside something larger. Inside the local group. Inside the Lania Chaos supercluster. Inside the cosmic web. Inside the observable universe, which is itself presumably a small fraction of the universe as a whole, which may itself be one of many such universes in a multiverse whose existence we can barely speculate about. You are nested inside structures, all the way down and all the way up. From the atoms of your body to the cells they comprise, to the organs those cells build, to the organism those organs sustain, to the planet that organism inhabits, to the solar system that contains the planet, to the galaxy that contains the solar system, to the supercluster that contains the galaxy, to the observable universe that contains the supercluster. Every one of those levels is real. Every one of them has a history. Every one of them is changing, on its own timescale, in its own way. And you, at the particular level of the living organism, are the level at which all of this complexity has, in one extraordinary instance, become aware of itself. The carbon in your body was forged in stars that died before the sun was born. Their supernova ejecta mixed into the interstellar medium of the young Milky Way, incorporated into molecular clouds, collapsed into new stars and planets, delivered to the surface of the Earth by the processes of planetary formation and geological cycling, and eventually assembled, through 4 billion years of biological evolution, into the molecules of your cells. The iron in your blood was made in the same way, forged in stellar cores and scattered by supernovae and mixed into the Milky Way's chemical record over billions of years of stellar evolution. The oxygen you breathe, the nitrogen in your DNA, the calcium in your bones. Every atom of your body that is heavier than helium passed through at least one stellar interior before it reached you, and many passed through several, over the course of the Milky Way's long chemical enrichment history. You are not merely inside a galaxy. You are made of it. The Milky Way built you, from its own processed material, over 13 billion years of stellar evolution and chemical cycling. When you look up at the Milky Way on a clear night and see that band of soft light, you are not looking at something external to yourself. You are looking at the factory that made you, the source of your atoms, the origin of your chemical complexity. The galaxy is not out there. It is in here. In every cell. In every breath. You carry the Milky Way inside you. You always have. And it has been changing, slowly, over the entire time. Long before you existed. Through the merger that built its inner halo 8 billion years ago. Through the formation of the thin disk and the long, steady evolution that produced the chemical environment in which the Sun and the Earth formed. Through the 4.5 billion years of solar system history that preceded your birth. Through every generation of your ancestors, who also carried the Milky Way's atoms in their bodies and also looked up at its light and also wondered, in whatever way was available to them, what it was. The wondering is part of the galaxy's story too. The Milky Way is a galaxy that, in one small corner, after 13 billion years of evolution, produced creatures capable of understanding what a galaxy is. Of measuring its age and mapping its structure and reading its history in the motions and compositions of its stars. Of sitting in the dark and spending 3 hours following its story from beginning to foreseeable end. That is extraordinary. And it deserves to be noticed. You noticed it tonight. For 3 hours, in the quiet dark, you let the galaxy tell you its story. That is a rare and remarkable thing. Sleep well. The galaxy will still be there in the morning. All 100,000 light years of it. Turning slowly. As it always has. As it always will.